We're up. Okay. So I don't think everybody who registered is there. Um, but maybe in the interest of time, we should start. How do people feel? Hey Tara. Yeah, so we are recording and we're also now live on YouTube. Excellent. So, ah, here we have some more people coming. And I think we're gonna start. How do you feel? Bina, are we ready to go? We are so ready to go. Um, while I'm presenting, can one of the other co-hosts please keep letting people in? Sweet. All right. If I just find my slides and then find you again. Okay. So, welcome everybody. I hope this is going to be really fun and we're going to learn a ton. And I have prepared like a really brief intro just to get us going. So this is Unfold in Julia workshop. We actually have like a little Easter egg here. So not only is Bene presenting all of the stuff here, but we also have Olaf, who is another originator of the Unfold Toolbox in our meeting. So hi, Olaf. Thank you for joining us. We're very happy that you're here too. Okay. So who are the people who organized this workshop or who you're going to see today? Well, the first person you have to put up with is me. I'm seeing you from the University of Birmingham, the Center for Human Brain Health, but I'm really not that important. I'm just clicking buttons today. The people doing the actual work are those people here. This is Bene and his lab. So you have Bene, Judith, René. I don't actually don't I is it Jeffrey? Yes, okay. Martin and Vladimir. And you can see what they're going to be doing. Bene, Judith, and René are going to give talks today. And I'm going to show you the program in a second. Maybe you've already seen it on the website, which, by the way, has been made perfectly by Judith and René. So thank you so much for doing all of that. All right. Who do we have in our meeting, or at least like who did we have sign up? Oh, yes. So here are our wonderful presenters today. And tutors. Okay. Who are you? You are from all kinds of places in the world. Thank you for giving us that information. We're really happy that you're here, just admitting more people. And as you can see, a lot of people are from Germany, the UK, and the US, but we really have people from all kinds of places. And we're very happy that that is the case. Hopefully, there will be more people from more places in all those different time zones too, watching us maybe after the fact on YouTube, which we're making possible. All right. We have asked you um, about your coding experience, and I know at least one person lied about it. Someone who is definitely not a noob said they're a noob. So we have everything from noob to wizards. Very few noobs, very few wizards, and a lot of people in between. And thank you for giving us that information ahead of time. That has allowed our people preparing all the materials to calibrate accordingly. All right, we've also asked you whether you've used Unfold before, and really most people haven't. So we're really excited to, share the magic with you. All right. Without further ado, this was the welcome, and we might be able to start not too late. Um, I think one more point here. So you see there's a bunch of things happening. We have regular breaks, but every single one of these content sections actually will be also including a little bit of a practical thing where you do some little assignments. And during those assignments, I would like you to follow this chart. If you have a problem, think about whether you're comfortable asking that in public. If you are not, you can message me in the chat privately, ask your question, and then I'm going to decide what to do about it. You can also, if you are comfortable, just post in the chat to everybody. And then I'm also going to make a decision about it. So either I'm going to get somebody's attention to say, hey, can you quickly answer this? And we're going to explain it live if this is relevant to everybody. Or I might say, oh, actually, can you put this on GitHub? And we'll answer it there later. Or if it does require that somebody just works with you real quick to make sure that you don't get lost because there's an issue, we can like either answer it in the chat or I can move you to a breakout room. We're gonna have this up during all the exercises so that you know what needs to happen. Good? All right. Okay. Then I think we're ready to go. And I'm gonna hand it to Beta.
Hello. You should be able to see my slides now.
They're coming up.
Perfect.
Here we go.
Okay. So yeah, welcome. Very excited. I think this is going to be fun. Let's hope. And yeah, let's jump right into it. There's a question I get since moving to the Julia programming language. Why? And I get that a lot. And I think I start this workshop here not with the concepts of unfold and syntax or blah blah blah, but I just like the bigger picture of why did I move, and a little bit about the Julia programming language. I hope you now all installed it and that you all have been running the installation notebook. And if you want to, you could already. I have a slide to that later, but you could already start the exercise notebook, the first one. So it's starting up in the background, but it takes only 20 seconds. So why Julia? Julia is a programming language that is free. I come from a MATLAB background. I programmed the original Unfold is in MATLAB. I programmed a ton of code in MATLAB. But at some point, you have your own lab, and then suddenly MATLAB can be really expensive. So it's free, has other benefits, open source, etc. Right? The syntax was for me relatively easy, and I hope you will also not struggle too much with it. Please ask lots of questions. We have plenty of people to help out. But the syntax is relatively close to R, MATLAB, Python, so stuff that we in our community, I think, mostly use. There's a downside. It does not have as many packages as other languages because it's relatively young. But there's an upside. It's extremely easy to call Python packages. So there's a really, or R packages also. There's a really awesome package. It's like 10 lines of code that allows you just to use all of MNE just in Julia. It's really amazing. Even with plotting, etc., all the things work. Julia also has an inbuilt reproducible package management. I hope that by now everybody understands how important it is to have a reproducible workflow. And Julia just basically has Conda inbuilt, and it just works, and it's not slow, and I really like it. Maybe the thing that Julia is most famous for is that it's actually allows you to code very fast code. So it allows you to match the speed of C or Fortran without actually changing the programming language. There's this joke of how do you make Python fast? You stop using Python, you use C++ instead. And that's what actually happening. There are big packages that are 80% C++. And the problem, of course, then is we are all not computer scientists, not research software engineers or something like this. So if we hack together our small code and we want to share it, it's probably going to be slow, or it's probably going to be in C++, and then nobody else knows C++ and can maintain it. So this is the two language problem that you want to have. On the one side, you have one language that is high level, as MATLAB or R or Python, and the other one is something that's fast, that allows you to do all kind of optimization. And in Julia, you just have both. And that, yeah, as a toolbox writer, this is really amazing. You don't have this np.diff, np-mult thingy from Python. It's like in MATLAB, everything is just natively, linear algebra is just inbuilt. You can do fancy characters. I really like to have that as well. So the algorithms, they have all the same names, etc. It's really nice. And yeah, as a developer, coming from MATLAB, I guess every language is great in that sense, but you have unit testing, you have documentation, all these things that are they are easy to use, and there's nice inbuilt thing. And to highlight this point of speed, just one plot here. So this is a bunch of differential equations, and you can see in colored implemented in different languages. And this is not a point of oh, there's a better implementation or better algorithm or something like this. These are really partially like this Fortran C code. They are made for that, very much that problem, and Julia can still blow them out of any leak, right? In this case, they're more obviously Julia is not the fastest language for everything. That's not the point. The point I think you should take home is it is possible to write very fast code in Julia, and who does not want to have the result immediately instead of waiting 2 hours for your cluster permutation test to finish or something like that. Let's also ask the people who created Julia what was their goal. So they wanted to have it open source. We have that. They want to have the speed of C. They want to have an obvious familiar mathematical notation like MATLAB. They want to be, in principle, able to have as general programming as Python. They want to have the easy statistics of R and the powerful linear algebra as MATLAB. And they also want to be able to glue programs together as a shell. So they just wanted to have everything. They wanted to be greedy. And yeah, I think they succeeded, and I really like Julia. It's just a fun programming language. There was an event, though, that started of how I even arrived at Julia. Not only was I a little bit annoyed about the MATLAB tooling, which is really terrible, but I dabbled a lot around with mixed models. And here's just a comparison. So this is calling R from Julia, actually, but the overhead is minimal for just any linear mixed model. If you don't know what this is, it's just something that takes time to run a statistical model. It takes 1.5 seconds. And in Julia, it just takes 30 milliseconds. So it can be, in my experience, up to 100 times faster. And this is what I'm interested in. Yeah, you can do much more things, especially if you want to fit in a linear mixed model. So each time point, you don't have to wait ages for it to finish. It's just 100 times faster. Awesome. Little bit of things maybe that are helpful to know if you're switching to Julia. So it's just some oddities I try to collect here a little bit that will maybe throw you well, I don't know the phrase now. In MATLAB, if you come from MATLAB, you know that you can broadcast things. So you can write a dot plus, and then it will do the element-wise addition. In Julia, you can also do that. You even have to do it. It doesn't automatically, like MATLAB sometimes do it. So if you want to add element-wise these two vectors, then you need to write a dot. It means to broadcast or element-wise. But the cool thing is you can also do that for any other function. So if I want to apply this function to 1, to 2, and to 3 independently from each other and then collect it back again, you can do that for any function. Oh, and here there should also be a dot. Now I missed myself, because you could also do it for inbuilt function, for any function, right? So that's nice. There's one oddity, maybe you'll stumble upon it today, maybe not. But if you ever want to concatenate a string, you need the multiplication. And the idea is that multiplication in terms of matrix notation multiplication, you cannot just switch the order as you can with the plus, right? And for string concatenation, you can also, yeah, okay. It's a bit weird. I don't know. You just need to know it. It's a little bit like if you do if or for, etc. It's like in MATLAB, if and end. One nice thing that threw me off a lot and when I was starting to learn Python is that you never know when some object is modified in memory, so in place, which is a nice thing that MATLAB can't do, but it's very helpful. And in Julia, by convention, you always add this exclamation mark. So if you're modifying something in place, then this will be a modification. So let's say you create a model and then you want to fit the model and you don't actually assign it and need to assign it anything because the data is changed in this object of M. Julia can be as programmed as dumb as MATLAB at times, but it also has is smart and has this like maybe if you come from R, this kind of object-oriented, like it's not really objects. I shouldn't say that, but for our purpose, I think this is fine. And here are just some commands, like you can find out what type your certain variables have, what kind of methods are available for that, or what kind of field names you have to discover a little bit of structure. And finally, I mentioned this, if you want to be fancy, you want to have this kind of LaTeX style characters, you just write \LaTeX commands like gamma, whatever, and you can press tab and it will autocomplete to something like that. That will works pretty much everywhere. Okay, this what I wanted to say to the Julia end, and now I don't even have the schedule here. Let me briefly pull it up. But it's not a Julia workshop, right? It should be an Unfold workshop. We just use Julia to have some sane environment to do things. Okay. So what is Unfold, right? That's a big question. In the first place, I guess you're all kind of familiar, else you would have not registered. And I think the big insight maybe is that every ERP you have ever done is kind of already a regression. And so if it's a regression, why not just use regression in the first place? And Unfold is a toolbox that supports you in making this step relatively easy so that you can apply a regression to each of your time points, to each of your channel, and then, deal with all the conceptual issues that regressions have, but you at least moved one, generalized one step from your averaging from your ERP. So you can really, like, this is the way I also think mostly of it. Think of Unfold as the step that replaces the mean function that you typically do to calculate your ERPs, right? And then afterwards, you will again get something like an ERP, like you get after the mean function. But, well, the intermediate step is a little bit more complex. There are these two papers that I will recommend to read. This is the Smith and Kutas paper on which kind of introduces this regression ERP framework. And there's, of course, also our Unfold paper that you can also read, also gives, I think, a nice introduction, but this is the OG thing. And then if you want to go for something, if you're more from auditory or so, temporal response functions are a concept that is extremely close to our ERPs, but I will not discuss it much later. If you have specific questions, happy to discuss them as well. So there's this Unfold toolbox. There's a MATLAB release, and I briefly want to talk to this. This is work we did with Olaf. We spent many hours figuring out all the ways we wanted to do things. Right now, we are mostly fixing bugs. So if you have a new feature in MATLAB, please feel free to make a pull request and say, oh, this is this cool new feature, I want to add it. We will happy to support you, but we are right now not actively developing this, and in the Julia version is actively developed. And by now we have more than 20 contributors to our family, Toolbox family, to our ecosystem. So thanks a lot for everyone who's doing work here, developing, raising issues, also contribution, just providing feedback is also contribution. So thanks a lot. And sorry if you don't appear here. I don't have a central list. Unfold JL ecosystem. We have this really nice documentation website now where we are collecting all the tools that we have. Right, you can check it out maybe after the talk or during the exercise or something like this. Right, so you will find plenty of information, also a little bit of general overview of other RERP packages you can do. And here is a little bit the whole family, how it's going. Yeah, there's this main toolbox, I would say. This is the Unfold.jl toolbox, which has most of the features and some more from the MATLAB Unfold. It can be put on the GPU, right, where it's over 100 times faster. So even big models can now be run in less than a minute. So this was one of my goals to do. You can run it from Python as well. Not everything is as smooth as from Julia, but it's absolutely possible. There are tutorials, and you have the real marginal effects, which I think is an awesome feature. You also have a mixed models package. There will be 5-minute lightning talks at the end of today in the afternoon about this toolbox here, about our plotting library. This is from Vladimir Mikev. We will have a lightning talk. Judith has even 2 toolboxes, but just one lightning talk. There's like a stats toolbox that gives some tutorials of how you could continue on with your data. But her main work is on Unfold Sim simulation toolbox, which we will use throughout the workshop in a hidden way, and she will also have a spotlight on that. And then we already have an Unfold Bits tool, so you can run it. If you have a bits data set, you should be able to run this relatively simple and fast, thanks to René. We also started to have some overlap corrected decoding code. This is a little bit more work in progress, but there are 2 algorithms now implemented, which I think are interesting, but we have to really, like we as a community, have to look more into how we can actually do this properly. If you want to move to Julia, right, we are always happy to support any transitions to it. An ecosystem lives by the community, and so we are happy to grow this. And this is one of our steps of how we try to do it, giving this kind of workshop. So this is close to the finish of my introduction here. So what's up on today's agenda, right? We will deal with Unfold.jl. We will deal with this formula here. Don't worry, we will have a slide later on this. We will also deal a little bit with eye movements and brain, because this is my viewpoint of how I even reached to regression ERPs. So the first big point is regression ERPs. What is that even? And of course, it's the future of ERP analysis, right? No, I mentioned it before, it's a generalization, so that's nice. And then we will have an exercise that you all going to do. We will have a break, and then we're going to go for the second part, which is continuous predictors and marginal effects. So this is really of finding the power in breaking all the boundaries you have and how you think about what kind of EG experiments can be done, because continuous predictors are notoriously difficult to analyze just using means, and you need more powerful things, right? Afterwards, we will go one step further. Instead of just continuous predictors, we will have nonlinear continuous predictors, right? So this is even cooler. I have the small animation here where we fit either in linear or then even a nonlinear effect to the data. All of them work, but only one of them is correct. And I think if you work with continuous predictors, it will be rare that you actually find a real linear relationship. It's will be most of the time it will be a mix of several different things, maybe. Yeah. Finally, this is like the main working horse, I would say. This is the overlap correction, because if you are in this framework, it allows you to push it even one step further and look at completely new data sets. I mentioned eye movements before. This is what we will be doing. But you will, like, even if you have a very simple EG experiment where you have a stimulus and a response, then already you have overlap between the activity of the response and the activity the stimulus generates. So you already have to take care of that. Yeah. Okay, cool. We are great in time. I have 2 more minutes. If there are already questions to this first part, maybe about Julia or I don't know, then I guess somebody would need to ping me or write me in the chat whether this is. Other questions?
Nope, we're all good for now.
Okay, cool. Yeah, I can also open the chat now. Can click. There it is. Yeah, this is a great question. I see the chat now, sorry. And I have a minute to answer that. Yeah, so it's real that Julia is so cool. There are minuses I have not been talking about. One of the minuses that Julia is a compiled language. What that means is that whenever it sees some of your code for the very first time, it takes a little bit, it takes a while to to, well, first figure out what you're going to do until it makes it fast. The second time you're going to do something, then it's going to be fast in the first time. That means that whenever you start a new Julia process, like a new notebook, if you had, or a new, well, just a Julia process, then loading a package the first time will take much more than you are used to from MATLAB or from Python, which is a more interpreted language, right? So this is one of the stumbling stones, I think, that people, it got much better, but you cannot just open Julia and then immediately plot something. You need to wait, I don't know, 10 seconds or something. By now, it's not that bad. If you have a lot of packages, it can be a minute that you need to wait, but yeah. Yeah, I hope that answers it. Like, this is for me the downside and the downside of the smaller ecosystem. Yeah. And the question for Tara, yes, you understood correctly. There's also a MATLAB toolbox. It also has unit tests and documentation, etc. Yeah, but as I said, there are more and newer feature in the Julia one, and they both they have similar principles, and they have also the MATLAB toolbox has some benefits. I think that it's a little bit harder to reproduce in Julia, right? It goes both ways. Okay, cool. I'm going to continue right on time. We are on schedule. I think that's the first workshop I give where this is possible. We are now reached regression ERPs, and I want to give you a little bit of my motivation of how I even reached there. And I'm very happy that Olaf is also there, because, like, I think without Olaf, I would never sit here in the first place. So I'm generally interested in eye movement in the visual sense, and we do eye movements all the time, right? So this is a video here done with Anna Gerd, and you can see there's a person just in a shopping mall looking around. So this blue dot that you have here is the current gaze fixation. But the person does also many other things. It moves around, right? It makes decisions, etc. So there's a multitude of things happening all at the same time. And I started out with this: how do you even start analyzing something like that? What do you do if people move their eyes, right? You have all bunch of problems that I will discuss in a second. But why is this important to allow people to have natural environment? And I think, yeah, all of these things, if you're interested in any of these, like, I don't know, mobile navigation, VR, gaming, reading, talking, if you do something with infants, something with sports, etc., you all need to break out of this really reduced lab setting, and you need to allow for eye movements, you need to allow for other motion as well. And I really think that Unfold is one step closer to that. I don't think we're reaching there yet at all. There's many limitations, as always, but it's probably better than taking means of ERPs. But I'm very excited to see what other people have are coming up with. Any case, eye movements are super important. So if they are also super nice and cool things. So if you here recorded my eye looking at some kind of poster, I could record EEG at the same time, and then I can use the stable periods, the fixations, I can use as event markers in my EEG, right? And that gives me, suddenly I have 4 trials per second, so a huge amount of data. I can cut it. I can do very beautiful plots and contrasts with something like that. Well, the problem, and this is something, again, back with Olaf. Olaf described this way before I was ready to do something like that. There seem to be like 4 problems that we have to address in order to be able to do eye movement and EEG in the lab now. This is not even in mobile. First of all, you have to integrate the data, so you have to send all this, the triggers around. You also have this muscular artifact, not like the dipole artifact of the eyeball moving and then moving a lot of charges around, and so you get these huge artifacts from blink and from eye movements, so you have to correct for that. But then you also have this, what I mentioned before, this overlap problem, and you have this nonlinear or linear covariate problem as well. And I think these 2 things are pretty much solved. So with lab streaming layers, with triggers, also people know how to, they know how to do that. And for this one here, we have ICA, and especially for eye movements, Olaf has this really cool algorithm, OptiCat, that optimizes ICA for eye movement. So I really think these are done, right? No, not 100% done, but we have a good enough version right now. And these were not, and so this is why back in 2015, I think we met and we came up with Unfold with this regression ERP framework, trying to address this issue. Okay, this is my motivation of how I look at this field. Now let's have a little bit of motivation. I mentioned before that that the mean and is just a fancy regression. So let's break that up a little bit. Imagine you have a kind of I have to close the chat. I'm getting distracted. It was a pupil lab side tracker, just for interest. Imagine you have like this kind of free lab setting where you're allowed to move the eyes, and you can move the eyes on faces or you can move the eyes on bikes. And that's the general example I will give throughout the experiment. And let's say you're interested in something very, very simple, just the P100 for faces versus the P100 of bikes. Does that make a difference, right? Whether this is a sensible question, I postpone, but there's typically some kind of contrast of interest. And now we're gonna find a complicated way to write exactly this thing, right? And this is based on a linear model. So basically, this notation here tells you, okay, let's take the P100 of a phase trial of the of the first phase trial here, and we can write that as a sum of 1 times just the phase beta plus 0 times the difference between bikes and faces. And bear with me, this might, like, if you have never heard about linear models, this might sound a little bit insane, but you will see there's a logic to that, right? So this is the sum of it, plus there will be some error that's specific to that one trial, right? Because you will have other trials, let's say here, a trial of a bike, and now you also take the phase beta plus 1 time the difference of the bike minus the phase. Right, so this together gives you then the activity of the P1, and then you don't only do that for your 2 trials, but you have many trials, many repetitions. And I now notice that I have a car here instead of a bike. Sorry for that. So you have different trials, right? And some of them are faces, some of them are bikes. And now you can take out basically this notation here and put it in this kind of matrix, and we will look at that later in the next section a little bit more detail. And you can put out these parameters that you don't know yet. This is this is kind of giving you the ERP. You put it in here, and now you have a vector here of errors, and this error you just you just try to minimize it as much as you can. I don't want to go much more into the detail here, but in the end, what you want to learn from the data is this. This here, called the design matrix, sets up the structure of your data analysis. Here is a very simple structure. We just have 2 conditions, so we just have 2 columns here as well. Exactly. You can also summarize this a little bit in this matrix notation. I will also show that in a second. And now where are now the means encoded? The means are encoded in this beta here. This is this mean here, right? So this beta here is the mean. And this beta here you get by adding these 2 parameters together. And that's the complicated way to write your mean. And that is one way how the mean and the linear regression is related. And this will give you exactly the same results. That's my promise. But now, why bother? Why making this so complicated, right? It's a very good question. And sometimes it's just not needed because the results will be completely identical. But you could have here, especially if you do an eye tracking experiment, you could have, for instance, have some continuous confounds. So maybe you like bikes more than people, and then you do larger eye movements on bikes than on faces. And if now an eye movement also makes a certain response in the brain, then you might get just a confound simply because people do larger eye movements. Or there could be also an effect that Olaf described. There could be an effect of stimulus position, because if you look at the left side of the stimulus, then suddenly you have much more background here. Then if on the right side you have much more background here. So you could expect some kind of lateralized activity as well. Okay. What you take away from this is mean and regression is similar, and regressions are awesome, and they have this kind of different things. like the sign matrix, and they have the parameters. And we will now go for, yeah, we will now introduce time into this whole dimension, because typically you don't only interested in the P1, but you, like if you could think of calculating an ERP, you get a curve over time, right? So you don't only have one time point here, but you have many time points for each of these trials. So these are our single trials. Also, typically, you don't want to build this design matrix by hand, but you use what we call the Wilkinson formula, and I will have a little bit more detail about that later. But basically, it just means this is the left side, this is your trials, and these are proportional to your right side, and this describes your design. The one is always the intercept. It's a little bit complicated. I will not go into details here, but now you heard it. This is the intercept, also sometimes called constant. Okay, so we have this data here. Let's pick one of these, like we had on the previous slide. We're just going to do the same thing that we had on the previous slide, so nothing new per se, except that we have more time points here. We're also going to build this design matrix, so you're kind of familiar with this now. You have the intercept and you have the difference of the one condition to the other one. You have the parameters here, you have the arrow here. And now we already fitted basically this one parameter, and we get one value for your beta. And now what we simply do is we repeat this for each time point. We shift it over, and at the same time, we get this ERP curves. And now, because of the special coding that we are using here in the design matrix, and that coding is important, but I don't have too much time to talk about this. Because we have the special coding here, this first column is an actual ERP you would get for the face. And this one here, because it just is the difference, it just has a 1 whenever there's a difference of when there's a bike. This is actually like a difference curve, like a difference between two ERPs, basically. What you should also be familiar. So both of these things are already familiar, and yeah, I hope that yeah, you can kind of appreciate that. So now I did discuss this Wilkinson formula a little bit. Let's have a look a little bit in more detail, because yeah, oh, this should be to the one. Sorry for that. If we think of this left side, it's not so important for us. But if you think of the right side, that's more important. And what's a little bit hidden here is we are writing here some name, and this name will later be looked up in an events table you will see in the exercises and understand that better. So you have some kind of table, like an Excel table. You can think like a sheet, where you have on top, you have for each of the trials, you have, let's say, a stimulation, whether you stimulate it with a bike or with a face, and the size, maybe the size of the stimulus can be changed, and large and small, etc. And for each trial, you have an entry, what the actual level is it. Maybe this is big, middle, small, and maybe this is bike and face. And so now the Wilkinson formula looks at this formula, what you want to model, and it looks at the event table, what type of variable is there, and then it actively directly takes this information and generates the design matrix for you. So there's nothing more you need to specify than providing the events table you have and this kind of formula. And if you then later want to have a different model that doesn't take size into account, or maybe even takes the interaction between these two things into account, then you can simply modify this formula, and that's quite nice, I think.
Bina, we have a question in the chat about the intercept, whether we always keep it equal to 1, or whether there are other designs that require other numbers for the intercept.
Okay, yeah, it's a good question. The intercept is really special, and it is always 1. There's no, like, I'm not aware of any. What you can do is you cannot use the intercept. So in this matrix here, what you could do is you could have a column that has 1 only when the faces are, and a 0 when the bikes are. So like the different how do you say, the complements to this column here, and then you would get 2 ERPs, 1 for the bike and 1 for the face, and no difference curves. But as soon as you add more effects here, like not only is bike but many other effects, then an intercept is typically something that you would want to have. This column here, and we will see that also in the second part, this does not typically does not need to be zeros and ones. This, if you have zeros and ones, it's called dummy coding, but there's also a way you can have effect coding where this would be -1s and 1s, and it has certain benefits in interpretation. But yeah, I'm skipping this for now, even though it's an important comment. I do have it somewhere on the slides later. Yeah. Thanks for the question. It's helpful. Okay, a little bit of history of all these kind of things before we go to how you actually do that in Unfold.jl and how you yeah. For another talk, I put together this. I tried to find out what is the rules of these different thoughts that we have here for regression, ERP, etc. When were people first doing this? And this is just, I think, to highlight that this is Unfold. Sometimes people say, "Oh yeah, I unfolded this" or something like that. But this is like really many people have been using these kind of tools before. We are of course very happy if you do that because well, it sounds also cool to you can unfold your potentials, right? This is our tagline. But yeah, please be aware there are many other people who have done it before, and we are not. We are standing on the shoulders of giants. We basically just put it together in an easy to way use. Just okay. And also be aware there are many reinventions, and so different like these things are pretty much all very, very related and similar, but they can have extremely different terminology because they come from very different views of the world. I'll put that up here. You can look it up later, but this is more for reference. I don't want to say more about this here. Now let's have a look of how we are going to implement such a model that we had that we just did. How hard or easy is it to do that in Unfold? And first of all, you're going to start with some kind of data. And if you're an EGLab user, then this kind of array should be very familiar for you because it has the same EGLab kind of structure. You have channels, you have time points, and then you have epochs. Right? If you have only 2 dimensions, then typically we have only 1 channel. And this is also the same. For most of the exercise, we will only work with 1 channel. But there's also like an advanced question where you could play around trying to get this to work with multiple channels as well. So this is our data. This is just a straight out floating numbers array. And what we also need is an events. This is a data frame. So this is like a table that you have that you will also immediately see in the exercise. It will contain, I was discussing this before, it will contain the information about each of these epochs. What kind of epoch is it? Is it a large, is it a bike, etc. Finally, the last ingredient you need to define the model that you actually want to fit. So in this case here, we are using this funny syntax called add formula. And the add, for people who know a little bit more about programming, is like a macro. So it's like a meta programming tool. But for most people, we don't care. Just this is the syntax. You also need to write a 0 because we are providing the data extra. It's not in the data frame, so we don't want to confuse the computer. And then here you write whatever linear model you have thought up. Then you put it into a fit command. You tell it, I want an unfold model. Don't fit me a linear regression or something like that. Unfold model, that's what we have. Formula, event table, data, and then we have a times vector, which is just a kind of like a convenience. So the output is a little bit nicer, so we know when in time you are. And that's just a vector, like eg.times in some sense. Right? Once you have that, you can get the coefficients in a matrix format like this, or as a table format like this, and there are many other tools. But you will also, you don't need to remember any of this because in the exercise we prepared it for you, and you should be able to do it. Okay, how do you get to the exercise? Oh wait, is there a question before? Something I should need to answer?
Oh, we're good.
Okay, cool. Yeah, Rumi, you can just write me in the chat, in our chat, and then I will see it, and I can check it there if there's a question. Okay.
Okay.
So now what you need to do is something that I hope you already done before with the installation notebook. You need to go to our website. You need to go to materials. Then you need to copy this first notebook to your clipboard. You need to have Pluto open and put it in this open a notebook file. You need to say, yes, I understand this is from outside my computer, blah, blah, blah. And then in the top, you need to run the notebook code. This will take like, yeah, between 5 and let's say 40 seconds, depending on how fast your computer is to start up. And then you can actually independently on your own run through the workshop material, the first exercise. For this first exercise, you will have like, well, there's a clock. So yeah, you have until 11:30 plus then 15 minutes of break. That's kind of our deal. So you do have some time to do it. please, Romy will put up the slide of how to ask questions, and then, well, we're going to answer them one-to-one or in GitHub, etc. So make use of this. We are here the whole day just to answer questions, basically. Yeah. Okay, cool. I hope that was a good chunk of information and that you then have fun and enjoy the exercise.
All right. Bene,
Let's hear it.
we have a question. And I think that's been coming up more than once. So, question is, are we supposed to run the code inside the notebook? I can only run the whole notebook, not individual sections. Sorry, never worked with it before. So I think that's a bit
Mm,
of a
mm.
Pluto thing.
No, absolutely, absolutely.
Yeah. Do you want to maybe
Yeah, I will briefly say something about this. This was also already a question in the morning as well, in the GitHub issues. The thing is, the Bluetooth notebook works differently than a Jupyter notebook. So in a Jupyter notebook, you can run each of the cell independent from each other, which you cannot do in the Bluetooth notebook. In the Bluetooth notebook, two cells always depend like if you have a variable, you define it in one cell, and then you use that variable in a second cell, then they will always depend on each other. So that if you change then the variable, the other cell will also automatically be changed, right? Oh, and sorry, GitHub discussion, yes, of course. Uh, I don't know. I mean, I could briefly show that, but I think it's also this is kind of like part of the first question in the notebook. But of course, if you're already irritated in the very beginning, then you will not reach that. So the first part should deal with exactly this kind of concept, and it allows you really nice to use this kind of sliders, etc., in the exercise.
yeah, this is actually one reason we went for Pluto rather than some other notebook, right? You made it sound like a bug a little bit, but that's actually a
Ah,
feature.
no, no, no. This is like I stopped using Jupyter notebooks completely, and I only use Pluto notebooks because I was always so annoyed that you restart a notebook and you forgot to put the cells in the right order, and then like you're lost, right? Um, I really like that. Uh,
Thank you, Bina.
Thanks for the question. Also, it's always good to answer ask these things early.
Okay, it sounds like we still have some people compiling the notebooks. Um,
Yeah, I will deal with it.
um, so that's a question. So how long it would take. The question is which notebook that is. So you all should have run the one for the setup before the workshop, right? Like, so there was something with in the installation instructions and that you should run before. So is it that, or is it like the next one that is like taking a really long time? Um, Okay, so you did run the other one before, and that took like a really long time during the installation. And now the Mass Univariate one is also taking a bit.
Romy, maybe you can just put me in the breakout room, and then
Okay. We're doing the breakout room thing. That's really exciting. So, um, okay. And where are you, Beta? So we have a question here about a theoretical question on the formula used in the notebook. And I think this has come up before in a private message earlier. Why is the bike condition the intercept? Does one of you maybe want to clarify or take this? You did?
Yeah,
Cool.
I can do it. Can you hear me? Okay, so first of all, it's not a silly question at all. It's just a bit hidden in the function because it depends on how the variable is coded, so like how it's represented. And by default, it's a dummy coding. So one of the levels gets like a 0 and the other one a 1. And like if you remember the formula, it's like this intercept plus the condition, and then for the level where there's only a 0, there's only the intercept like left, and therefore it's like the that means like the intercept represents this condition. And then for the other condition, there's a 1 in the coding, so that's like intercept plus 1 times the coefficient, then represents the other condition. I hope that helps. Otherwise, I try to say it in other words or write it down again.
Does the S mean we're good? Okay, I guess it does. Cool. Thank you, Judith. We have a follow-up question. What if you have more than 2 categorical variables? How would you determine what is the intercept and what is 1? So this is all contrast coding, essentially. Anyone want to take contrast coding? All right. Are we not? Are we making this a meeting room thing? Because I think this might be relevant to multiple people. I'm sure there's at least one other person that could use a little bit of explanation in this meeting. I have received private messages before.
I I must admit that I don't fully understand the question. The intercept would always be represented by a 1 in the Wilkinson formula, right? And you can specify, like, maybe the question is what condition should be, like I mentioned that in my slides, that the intercept in this case was the face ERP. And now you could say, yeah, but how do I decide that it's face or bike? And for most things that we are doing right now, it's automatically, or I think it's by alphabet. So actually it would be bike and not face
Yeah.
in the code.
Benedict?
Yeah.
I think like that was the question before, like why, how to know that the intercept represents one category, and I already said like it's this effect coding with 0 and 1, and now the question was, but what if I don't have two levels but more than one level?
Sorry.
As two levels, yeah.
More than two. Okay, okay. Categorical levels, not category values. Sorry. Yeah. Okay, can I understand? Well, first of all, just to clarify, it's dummy coding with 1 and 0. Effect coding would be with -1 and 1. But if you have more, well, yeah, you will get n minus 1 predictors. And to determine what, okay, now I see. Okay, to determine which is the reference group, there's a specific syntax that you can use. So in R, you'd have to do it beforehand. And in Julia, isn't there even, I thought, well, maybe I'm writing too many notebooks. Yeah, there's actually an advanced tool thing that you can find in the notebook for one define a formula. What about contrasts? And there you can there's the second line. I'm just going to put it in here. Where you define the contrasts, and here let's say you have a condition called B, a categorical predictor called B, and this has, let's say, 5 levels or whatever, and you want to have the base level to be level set, and there you could just specify whatever your base level would be, and I think that should answer your question. But a little bit more documentation about this. If you just, can I put an image in there? Nope. Or Romy. Or
Yeah, but if you want to share your screen, maybe.
no, I don't think it's necessary.
No? Okay.
It's already in your exercise thing. I just need to be yeah. No. It's in the exercise. It's not from stats. I mean, the command is from the stats models documentation, but it's or maybe I misunderstand the question. I can't share in a simple image in the chat, unfortunately. Okay.
Fine. Yeah.
We can have a one-on-one chat. I think that's easiest.
Cool. All right, so we have a question about the minimum minimum overlap. We're gonna answer this specific technical question in a second. But in general, so unfold is not just for controlling for like stimulus overlap, right? It's also control or like overlap related to like individual stimuli. But it's also to control for overlap in you know, stimulus processing with like eye movement related things and like stimulus processing and stuff that is associated with like generating the response and stuff. So just quick note on that. So it doesn't, so then it's conceptually certainly not like just the interstimulus interval. It's like maybe the inter-event interval or something like that. Well, you said quasi, so you probably knew that. All right. And here we got the answer. It's the min overlap should be the lower bound of this interval, whatever is between the events. Thanks, Renee. according to schedule, we're now having a little break. Ooh, Olaf has turned his video on. Hey, Olaf.
Olaf, were there's two SMI eye tracker in your background there? Are you flexing?
Dang. Ah,
That's the SMI museum behind me. Still looking for a lab to give them to. So if you're an severely underfunded lab, I might have an SMI eye tracker. Just email me. Email me.
nice. All right, so we're gonna meet again in roughly 15 minutes. And I'll pop out for a sec.
Yeah, but please keep the questions running. Somebody will be around and to answer.
Excellent. Okay, I think according to the schedule, we should continue with our next session.
Romy, there's a question in the chat. I can answer that one.
Yes.
I think. So the plot ERP result plot, I think you mean, Britta means the one that shows the intercept and the simulation phase, like the 2 lines. Is that correct? Because I don't think there's no other plot ERP plot. Anyway, okay, so basically in this case, the intercept shows you the ERP calculated for the in this case, I think it's the bike condition, and the black line, the stimulation phase line, is the difference between the ERP of the phases and the bikes. Does that answer the question?
Can we get a thumbs up or down for René's answer? Is the question resolved?
I do actually have a question to René, because I was quickly doing it, and I don't get an effect of faces anymore. Did we break the notebook? Because I get a flat line for the for the face thing. Maybe I broke it somewhere. But
Maybe you
should
did. I still have it.
You still have it. Okay, so my simulation face is flat right now, but I don't know why. Okay.
Oh, the question is about the minimum overlap just popped
Yeah.
back up, but I think we answered that in the chat actually.
No, I will briefly show it. So for some reason I don't have a face effect right now, but I don't know why. But the question is, what does this slider here do? And basically, this slider introduces more overlap. You can see here that here you can already see that the next event is happening. So this is after, well, the time is off, but if I make this smaller, then I will get the next event already in. So this is the minimal overlap we have in the simulation, right? And if I put this to the default value, which is very high, then you don't see it because it's outside of your modeling window. I think that should explain it. But we will, in exercise 4, we will have much more on this overlap thingy, right? I hope that clarifies it.
Thank you, Bena.
Well, we are making notes, right? We're using all your feedback to improve the notebooks, because it's always hard to write, so to make it perfectly clear, these kind of things. Okay, you should be able to see the slides again. Welcome back, everyone. We're gonna continue. I don't see the slides yet.
I see them.
Yeah, but okay, this is I need my view. Okay. We're going to continue with the second bit. The first bit, well, now you're all warm. You're fit your first or maybe your 100th mass univariate regression ERP. So pat yourself on the shoulder. Well done. And I hope it was fun, and I hope you enjoyed getting the confetti, right? I do like to go back to that and just, you can press it again. It's doing it again. So that's fun. Anyway, we're going to continue adding stuff to the regression toolbox that we now started. We will discuss continuous predictors and what is called marginal effects. Let's get right into it. I need my timing. Okay. So if you think of regression, then you're actually not thinking of taking means, and you're not thinking of having categorical variables, but you're actually thinking of regression of lines, right? At least from school. So the idea is a little bit, you have this kind of regression formula here with the beta 0, like the offset here that I'm modifying here, and you have some kind of predictor, and you have a slope, right? That's the whole idea. And you've seen something like that in my slides before, so it's relatively similar to what we had. And maybe this x now, if it's a continuous variable like the contrast, or it could be the luminance, or it could be the size of a saccade, or whatever, then you would have the x here on the x-axis. And then you could have like the ERP amplitude now for one time point, 170 milliseconds or something like that. And then you could try to find what is the best parameter. Here I'm just changing the beta 0. What's the best parameter to explain my data, right? And you find the best parameter that minimizes the square distance of these things. And there's some theory, y squared, etc. But just find the best line that fits the data point. And that's kind of, okay, that's we know from school. And then now you can do the cool bit. You go from a simple linear regression to a multiple regression. So instead of having just one x-axis, you kind of have two axes that explain the data. Maybe it's contrast and brightness. And then instead of having a single line, you have to span up a space, so you have to have a surface here, right? A plane, I think is a better word. And now you still try to find all the parameters. So you have a slope in one dimension, slope in the other dimension, and you're up and down. You have 3 parameters now, beta 0, 1, and 2. And you're trying to find the best plane that fits all of this. And then, of course, you could continue on, right? At some point, now I can't show it anymore because more than 3 dimensions is hard to visualize. But you could just write it up like this. You can imagine that you have n dimension, n predictors. And then conveniently, like writing all of this out, this is really bothersome, but conveniently we are now landing at this formula that we had in the very beginning, where we have this matrix product, because having this multiplications and summing all up is nothing else than doing a matrix multiplication. There's a small animation, but we don't actually care how exactly it works. Just trust me that these are exactly the same things, right? Okay, we also notice that this design matrix, and let's have a look at how they look like. So this would be for simple regression here. You get the 2 parameters, should be beta 0, but well, next time you get the intercept and your slope here. And if you have multiple regression, then you just get an additional column in the design matrix and an additional parameter that you can analyze. Now, this is on one time point. We so far have always been discussing multiple time points here. So here it's now exactly the same thing. Remember, we had the single trials here, and then we had the design matrix. So now we add one column here, and we add a parameter here, and we get another effect here, okay? So here, how we define it in Unfold would be, you have this bike or stimulation condition, or here I even have the Unfold code, the stimulation condition, and then you just add the saccade amplitude as another predictor. And now, because in stimulation, in the data frame, you saw the events were either strings, whatever, bike or phase, right? So automatically, the underlying packages recognize this as a categorical variable, and here you have a numerical variable in there, and so it will automatically just put that numerical variable here in the column. Right? There's no additional logic involved here, right? And there's one more thing that I think is important to understand. This here, we were very much in ERP land. We had ERPs, we had different curves, etc. But if you have such an effect here based on a continuous predictor, suddenly this is a slope, right? Technically, this is a slope too. But this is a slope that means if I want to now later know what is now a difference of 1 degree saccade amplitude or 1 step on my brightness scale, then this would exactly be the answer. This is the answer. If I now want to know, but okay, my whole scale is from 0 to 100% brightness, what is then what is the whole outcome? Then I would need to take this effect times 100. So scale it up, of course.
And we have a quick question.
Yeah.
Does this assume exactly one saccade happens per trial and always at the same time? By analogy to the bike, like exactly one bike appears per trial, and we know when it appears, so the idea of an event-related signal makes sense.
Yes, so here, basically, you can imagine that we epoch the data to the fixation onset. So 0, wherever 0 is, maybe this one here in the middle, that would be any each fixation onset. It's of course simulated data here, and we later will get to the stage where we don't even epoch. We also let the RERP do the epoching step in the design. But this is the fourth thing we will discuss. right? I hope that answers the question. Else, please ask again.
Yes.
I again don't see the chat because I'm getting distracted.
No,
Thanks
no,
for-
no worries. We're all good. Very clear. Thanks is the last comment.
Okay, cool. Okay, so now we added one, and nobody in the world can stop us from adding yet another one, right? So now we finally we had this. Have confound control in some sense for saccade amplitude and maybe also fixation condition. Actually, in my simulation, fixation position doesn't do much, or it's less visible because maybe we have put this into pixels, and so now the max effect would be times 2,000 pixels or something like that, and suddenly it's big again. Who knows, right? It's just something to keep in mind. And we will address this issue of scaling, etc., with a very clever way with the marginal effects in a second. Okay, but this is, I think, this is all you do, right? You just add continuous variable, and it will try to fit this kind of linear effects to the data. Now, yeah, I did mention that the interpretation is a little bit more difficult, and we have a really cool tool, and this also will address a question about we had earlier about the contrast coding. What is my dummy level, and how do I interpret these coefficients? And so this will address this as well. And this is making use of predictions. So what we can do if we have specified this model here, and let's say maybe the x is defined by a condition and a continuous variable, right? What we can then do, we can inspect this beta. So this is this plot ERP that you have been all doing before. Now we added this continuous predictor. So this is how it would look like. You have the intercept, you have an effect of phase versus spike, and then you have this kind of slope, right? This is relatively difficult to interpret, and maybe because basically the slope is there, because this is different to what we typically have with the ERPs. And basically the question is, how do we get from here, from having difference effects and slopes, back to ERPs that we can understand? Right. What we can do is we can do a prediction. So now we get a small hat because it's a predicted EEG data. Here we had this arrow term, right? So this is the real data, predicted data just without the arrow. And basically for each of the trials, we could back calculate what does the model think that the trial looks like, right? And this would be something like this. This is how the model thinks each trial in a certain data set here would look like. Right, so you can clearly see there's a lot of the slope effect going on here because this is the only one that has big activity here, and you can also appreciate maybe here there's a difference, etc. The scale is very much different because this is now in data space in some sense, right? We could also inspect the residuals here, but I'm not putting there because I want to focus on this prediction, because this is, well, it's interesting, but it's not particularly helpful for what we are actually interested in. So let's look closer what we are actually doing here, right? If we predict a single trial. So this is the single trial with the arrow still, but if we want to have the y hat, then it could look something like this. We have our betas, and then we put in specific values that we want to evaluate the betas at, and then we sum it all up, right? So as matrix notation, you will see in a second y, and that's okay. This should be a comma here. Sorry, not the ... That's okay. You can write something like that, and you get for any single trial, you would get your answer. One issue is, of course, if you have many more predictors, then this suddenly gets very cumbersome, and also you can make errors. And people who have been doing fMRI analyses in SPM, they know this. They know the pain of writing your own, what's sometimes called a contrast, right? To write this contrast matrix and then counting how many zeros do I have to put so that there's one effect. Romy is saying yes, right? And I don't know how many errors in the literature are because of that. I assume there are errors because of that, because I did them myself, and it's just so easy to make a problem. So the nice thing is in Unfold, but also in other packages, there's like EM means package or the effects package in R or so, and there's an effects package in Julia as well. So we can use the effects function to just simplify this definition, and we can just say, okay, condition should be our phase condition, and my continuous variable should be 12.3 or whatever that one single trial has, right? And if you have one single trial, we could also do multiple trials, right? So multiple trials in this contrast view, you have to, for each of the trial you want to go, basically you have to build this design matrix and then evaluate it. Yeah, what we would want to do typically is actually going for multiple trials, but not the trials we've seen in the data, but like idealized trials, like perfectly perfect trials. What we can specify here would be that conditions we want phase and bike, and my continuous we want 3 variables, and then it's calculating all possible combinations of this, right? And we get an artificial new design, an artificial experimental result without any noise, perfectly balanced. Like that's what we want. That's kind of how I look at this kind of data. We want to have it balanced, right? And what the outcome of this would be something like this. So now I get 2 times 3, 6 different curves here. I plotted them at 3 different continuous values here, and with the 2
Dana?
different simulations. Yeah.
We have a question about how we decide which continuous levels we want to predict.
Well, now, because, given that you can do the prediction, you can just choose. This is just basically interrogating the model, right? There's nothing, we are not doing any new fitting or something like this. We are simply asking the model, okay, just calculate this sum, calculate that sum. So you can start with whatever range you think could be interesting to your problem. And then, well, probably if you add 100 continuous values here, your plot will be cramped again. But we will have, in the next slide, I will also have a little bit other display with more continuous values. And then you might be able to appreciate that sometimes having a minimal set is enough. Sometimes you kind of want to have more. I guess if you have a continuous, it makes sense that continuous effects have some kind of regular spacing to it. But it does need to. You can create whatever, and it's very simple. You will also see you can easily play around, and that's exactly also what we're going to do in the next exercise with these numbers, how many you display. And the plotting library we're using is very powerful, so you should be able to even cramp in 1,000 of these lines without a problem. Yeah.
And now, can you clarify again what exactly the ERP plot shows?
Mm-hmm.
So they're asking phase and bike at 1, 3, and 5. What?
Okay, fair enough. So this is not a coefficient plot anymore that we had before, but this would be if you could record an EEG experiment where you, let's say, have the phase condition. So we are on the dotted lines here, on the dashed lines. And you can record it with your continuous variable, which, let's say, it's brightness levels, 1, 3, and 5. Then you could say, okay, the ERP I would get if I only have this categorical design, let's say 1, 3, 5 with phases and bikes, then this would be my 6 ERPs that I would get. So this would be for 1. This would be my ERP. I could calculate with the mean for 3. This would calculate for 5. Except that this is not what we're modeling. What we are modeling here is that we have a linear effect here. So maybe even these numbers here never actually were exactly ran in the experiment, right? Let me jump back. Oh wow, all the slides at once. Let me jump back to here. Maybe you can see here in the brightness. We could now ask for a brightness value of 60, where there was actually no single data point on this brightness value, right? So we could have the data point somewhere else than where we evaluated. And here you can see if this would be really brightness, then this is more or less randomly distributed. But now we can make it to be really like perfectly balanced in a nice regular interval, as if this would be the data we actually produced, even though we, of course, did not produce it. It's a model fit. Does that answer the question?
Yes. So we have now clarified that the 1, 3, 5 is whatever you set as your continuous predictor. That's what it is referring to.
Yeah,
Yep.
exactly. Yeah. This is now really after the fit. This has nothing really to do with what kind of events you put into the model, right? The model is fit, and now we can just interrogate it for whatever combination of parameters we want to have. And yeah, what I really enjoy about marginal effects is that sometimes you just don't care about the continuous effect. It's just there for confound control. You basically just have 2 conditions like A and B, and the continuous variable might be different for A and different for B. Maybe there's like on average, because subject did larger saccades or smaller saccades or something. But you'd be interested in, well, how does my ERP look like if they would actually have exactly the same saccade amplitude, right? Something that is you could do matching or other things, but it's not so easy to say. But you kind of want to have this fixed at what we call the typical value, which is typically the mean of this predictor. And if you do that, so if I just cut out this thing and I just call the dict on condition AB, it will take the average of the predictor for all other non-specified ones, and it will give me just two curves here, right? So my marginal effect predicted Y has now two curves. Well, still car. I'm so close to have all the cars banned from my talks, but still struggling. But now we have two, and the continuous effect here is gone because I used for both of the curves to evaluate the average continuous value, right? And I can do the same. I could just remove the first one, don't care about the categorical predictor, but just have the continuous one. And suddenly I don't see the separation here anymore, but I just see in this case here, what is it, 10, 11 different curves, nicely delineating my linear effect. Right, so both of them are different calls, and you can just interrogate the model in all these different ways. Exactly, that you're interested in, that you're trying to understand this model better. Okay, does that make sense? There are questions to that? I hope this.
I think this is all good. I
Okay,
think.
cool. Because now we are at the stage where you are actually going to do that yourself. I already showed you the syntax, but it's also in the notebook, of course. So now it's time to start the second notebook and do your own marginal effect, do your own continuous predictors first of all, and then your own marginal effects, and try to understand well what does it mean to have a slope or continuous predictor in your EG data in the first place. Right? Okay, and I think Romy, you can put up the question thing again, and shoot with the questions.
So for anyone who's wondering, we will also be sharing the lecture slides. Bina, do we want to say, is this going to be on the materials website? That's a yes.
I'm exporting this minutes.
So on it. Always so on it. All right, Bene, welcome back. We have a question about syntax. Somebody's asking, what does let ... end mean? Is that so I can define the same variable again without getting errors?
Yes, exactly. I think this is the main purpose. So this is it's a local scope that you're opening that is not visible from the outside. I think that's the in Bluetooth, that's the whole thing. You notice that if you have multi-line thing, you need a begin and an end, but the variables you define in there can be visited from other cells. But if you have a let, then you can't. There's one caveat. If you change something in place, so you modify it, like you remember the exclamation mark, or you modify a column of a data frame, then Bluetooth cannot see that. So even in a let, it's not completely safe, right? So there can be some specific ways you could modify variables and then they still mess up the whole Bluetooth system. But mostly this is, for most reasons, you just want to have a quick plot and you want to use F for figure, but F is also a formula somewhere and then this just works. Yeah.
Thank you. Okay, I think we have a good question in the chat. Bina, do you want to say something about that?
Yeah, it's a tricky one. So there's no, I don't think we implement, René, do you remember? Or you did? I don't think we have R squared implemented somewhere. It's definitely on the list. This is like one of the 5% things that this the MATLAB toolbox has, that you get some indicator for each single subject of how well the model fit is doing. I mean, it should be, no, maybe, I forgot. I have to check whether it's implemented or not, but it's relatively easy to do because we have residuals, and then we can just check for each subject how much variability do we explain in the data. In principle, you should do that cross-validated, which makes it much more complicated, etc. But yeah, so there's no single value right now, because also I feel like it's very difficult to interpret. Let's just imagine you have you just, oh, sorry, many things at the same time. Let's start other. In a classical ERP, you typically don't have that, right? You have the only thing that you might have, people have started to use the standard error as a measure of uncertainty or quality of data. And this you also have available. So in the CoreF table, there should be a column called STD error. If not, then you can activate it in the fit somewhere. There's a tutorial for it. If you do overlap correction, then it becomes very quickly very difficult to do properly, because the standard error you can't use because you have temporal dependencies. And sorry, I'm taking this, I haven't explained what overlap correction is, etc. But just take my word for it. And you also have the problem that the R squared is biased. The longer you take your time windows, the more baseline you get, like 1 R squared for the whole model. So the longer you make the time window, the longer the baseline period gets. So you have always a bias towards 0 for the R squared, because in the baseline you don't expect to be able to explain something. Okay, so maybe a little bit confused and complex question. The direct answer is there's right now, I don't think any single numeric indicator, but it's actually a pretty simple request to have an R squared function, basically, that returns you temporarily resolved or potentially even for delta R squared for each of the predictor, how much variability it explains in the data for mass univariate models. For overlap corrected models, that's the thing that I'm working most with. For this, it's not so straightforward. Yeah. So I would plot stuff and assess it visually the same way you do it for traditional ERPs.
Thank you, Bina. Okay.
So,
So,
yeah.
lecture slides available just in time. Thank you, Bena. And I think our instructors deserve a lunch break. And
Perfect.
for anyone else for whom this is convenient, also enjoy your lunch. See you in a bit.
Bye-bye.
Bye.
How was the food?
Very good. I had a mushroom risotto. How about you?
I had a lentil soup and some fries and a salad.
That sounds excellent. If anyone else wants to post what they had for lunch in the chat.
I'm just waiting for teleporters to be a thing so we can all physically meet. It would be even more fun. Sven had some chicken.
Okay. I think it's about time to restart, huh?
I'm working on it.
Okay. We're ready for you.
Waiting in the wings. There we go. No, there, yes. Ah. Wait, I need to. If I want the video optimization, then I have to deactivate that multiple people can share. So this done. Okay. Welcome back, everyone. I hope you had a nice lunch. I heard some tasty food already. And yeah, we are back. We already learned mass univariate regression ERPs, including continuous effects and marginal effects. And I think this is all really advanced stuff already. And I think you should all be proud that you're still sticking around, right? But we will continue. There's no time to stop this train. We will only stop after overlap correction, and we will just jump right into it. And we will start next with making the straight lines that we had so far, these straight regression lines, bend a little bit, right? Okay, let's imagine you have a scenario again where we look at a single time point, because it's always easier to think of single time points. And you have some kind of predictor value, let's say saccade amplitude or brightness, contrast, whatever you fancy, depending on which field you come from. And this is the signal to be explained, so that could be the P100, for instance. Now, the underlying individual trials, as you can see here, they are not on a straight line, right? They have this kind of maybe logarithmic shape, or they could have any other shape. But in this example, there's not a linear relationship. You can fit in a line, but then, I mean, it wouldn't make much sense for some of these values. In worst case, imagine you have a quadratic relation, then the line would be flat, even though there would be quite a lot of relationship to the saccade amplitude. So wouldn't it be nice if we could allow this line to bend a little bit, allow this line to have different values? And one thing that people are doing is that they say, okay, maybe let's just bin the variable. So we're going to define one predictor that only models this trials, one predictor that models this trials, one predictor that models this trials, one predictor models these trials, etc. And then each of these will have a different beta, different coefficients. It's just 0 or 1. You're either in that group or in one of the other ones. And by doing something like this, so here we have predictors. We could sum up, and while there's now only one predictor available, and the other ones are all 0 everywhere, of course. So the sum, bear with me while we are summing here. But we're always summing. We have this matrix products, etc. But we can sum up and we can predict the signal, and suddenly we are closer, in some sense, to this underlying nonlinearity, right? So we moved from fitting one parameter here to fitting 1, 2, 3, 4, 5, 6 parameters here by making this by categorizing basically a continuous predictor. Now, the issue, of course, is that in biological signals, it's extremely rare to have this kind of step functions where you have a complete change of the variable. It would be nice if we could do something similar that we have here, but have like neighboring, like have a little bit of overlap between these categories, right? So that would enforce that we have a certain type of smoothness in our fit. And that's exactly what we're going to do. And this is called spline regression. So we're using, instead of using this like 0 and 1 boxcar basis functions, what we are using is a spline set. And there are many different ones. We are using the so-called B-spline set here for various reasons. Yeah, okay. I don't want to get too technical here. And as you can see, you have now different basis functions. They're non-symmetric and they are importantly overlapping with each other. So in order to predict the signal that we have here, you would need to sum all of these here together. What you're seeing here is actually already one step advanced, and you will look into this in more detail in the exercise, because this is already the basis function weighted by the model fit. So already weighted by the beta that you had, that you needed in order to get this curve here, right? The same, this was the same here. The actual basis set all have the same height, and then you scale it by the predictor you're estimating by the betas you get. And if you do that, then hey, this is great. We can get any more or less any nonlinear shape. Yeah. For those people who already know over and underfit, I will discuss that in a second. How does this now integrate in our general model of unfolds idea kind of model? Right? What we need to adapt is the design matrix. Instead of having one predictor for the continuous effect, we have to split this up into this basis set, right? So this looks like something like this. So instead of one, we now have, in this case here, 5 new predictors. And they will have certain value. Depending on this value that you have here, they will also have a certain value. So basically, you kind of look up what kind of what kind of overlap do I have? Where am I? And which of my basis functions is active as much? And if you then fit it, of course, then you will get also many more predictors here. And these predictors generally are not straightforwardly interpretable, right? You can look at one and then you say, okay, this one has a little bit of activity. It's somewhere in the middle. Probably in the middle, there's a little bit of activity. But because the neighboring ones can also always modify this behavior, this is not straightforward. And you guessed maybe you need marginal effects. Or one easy way to do it is to use marginal effects. And if you come from the MATLAB Unfold toolbox, there are not many, but I mention it anyway. This is kind of what we implicitly implemented there, also with the UF at marginal, UF predict continuous combination, right? But back then we didn't know better that this all called marginal effects, and in Julia version, it's a little bit more conceptually straightforward. We can look at this also in a different way. So this would be a design matrix. So you have the events here, or the trials, the repetitions. You would have one predictor that's just one everywhere. And then maybe this is a linear predictor, right? You see the linear formula here. And if you have a spline set, then, and this is sorted by the spline set, right? You have here, you have the very large saccades, and here you have the very small saccades. And you can appreciate that this is some kind of basis function just now flip to the side. So you look on top of the basis function, basically. Right, just a design matrix in the wild, basically. Okay, let's give you an example of why this is important. And here, Olaf, this is a study. This is a study he did many years ago, and we basically analyzed it with this tool, and it's published here in Journal of Vision. It's a nice paper. Check it out. No, it was fun to write, and what the task was here was people were presented with visual natural scenes, and they were just looking around. I think at some point a target appeared and they had to press a button when that happened or so. But the task is not so important. They just explored the stimulus more or less freely, right? And each of this fixation, I mentioned this before, we could take now each of this fixation and model it as one event basically in our data set. These events were modeled using 2 predictors. One is a spline for saccade amplitude. So this is also the way you would put this in. So instead of just writing saccade amplitude, you have to tell the tool, oh yeah, expand this to a larger set of predictors. And we are using spline here. You could also use, I think, you could use, for example, also a polynomial expansion or something like that for people who know what it is. But splines have better properties and generally are in favor compared to a polynomial expansion. Anyway, we are focusing on the saccadic amplitude. I will talk very briefly about the circular spline on the next slide. So if you do this and we calculate the marginal means, the marginal effects, this is what you already did in the last exercise. This would be kind of what we got for an channel OZ. And what you can see here is that if we kind of make the distances of where we evaluate the function similar, so this is a step of 5, a step of 5, a step of 4.5, you can see that the distances in the data here are not linear. Here, actually, they are linear, so at around 170 milliseconds, this is roughly linear, but here it's clearly nonlinear, and here again it's clearly nonlinear, but the reverse pattern that we have here. So, and I find that really fascinating and important that we can also over time then have the change from a continuous to a nonlinear to another nonlinear effect. It's maybe not surprising in hindsight, but I think it is absolutely important. And we were not the first one to show this effect here. Other people have shown it before as well. So that seems to be something that's quite well replicable. Now, I just want to show you a different, maybe then the connection gets even clearer, a different visualization of this effect here in the gray area, right? So we average over this time point, and we put now basically the color we put on the x-axis, so between 0.6 and 15, and we put the amplitude on the y-axis, and then you can see here, this is this nonlinearity that you can also visually see here as well, but now maybe in a more linear regression kind of style that you would typically look at it. It's of course hard to do because showing this plot for every time point is impossible. Okay, so at least in this paradigm, we clearly see nonlinear effects, and there are many of them, and they look quite nice. There are some individual fits, model fits. Exactly. I promise you also to talk about the second bit, and the second bit is a circular spline. So we also looked at the, you can make eye movements from let's say from the center to the top, to the right, to the bottom, or to the left, or from any point actually. They have an orientation, right? And so we just put the orientation as another predictor into the model. And now, of course, orientations are circular, right? So there's no difference or little difference between 359 degree and 1 degree. There's just a 2-degree difference. But if you would think of it as a linear effect, then they would be at opposite ends. So somehow we have to bend this x-axis basically around. And that's also possible with circular spines. I don't show the basis set here, but yeah, this is also implemented. And as you can see here, we do see this kind of circular effects also here at lateral electrodes. And if you make a saccade to the right, then the left visual cortex is more active. And if you make a saccade to the left, the right visual cortex is more active. And for up and down, it's a little bit more difficult to see. This is, of course, interpreting now this kind of 3 topo plots. We didn't do source localization or something like that. But you can equally well do more fancy things. And of course, you could also do your own basis set and various, also, other customized things, but this would be a topic for a different workshop. I mentioned before that right now, or if you notice here, we are always defining how many splines we have. And it could be that you put this number to a really, really high number, and then basically you have for each event, you have your own basis function. And then you get something that's called overfit. So each of the line is overfitting the noise, basically. Or you could have too few splines. So you try to model some kind of complex nonlinearity, but you have only available to maybe model a simple quadratic effect or something like that. And then you would get maybe out a linear effect, even though it should be something in between these two. And the really big and unfortunately unsolved question to some degree is how to choose this number of splines. The way we are right now experiencing our models, etc., is that if you stay below 10, and even I typically just take 5 or 4 splines, that seems to be right. I'd rather underfit a little bit than overfit a little bit. The good news is there is some kind of regularization over subjects, because you're fitting this model for each individual subject, and then you're going to average the marginal effects, for instance, over subjects, and that will regularize a lot of the overfits that you're getting. So there's some, we simply don't know, and of course it also depends on the quality of your data, the amount of your data, and simply the shape of your relationship, right? I do think that why do I then recommend to use like 5 splines or something like this? Because I think most of the relationships we have are not that you wouldn't expect to have a really crazy relationship in most of the data, or maybe you should, but we are coming from a world where we're not even fitting linear models, so linear relationships. So maybe we can slowly open up to more complex models. So this is the point. There are automatic solutions trying to address this issue. One is basically on cross-validation. This is already implemented in MATLAB Unfold. It is in principle implemented in Julia. We just have to write the tutorials, etc. As well. It's not particularly difficult. Actually, just some days ago, I asked a large language model to implement this for me, just because I want to see whether the large language model can do Unfold. Turns out they can, and they actually implement it correctly. So it's not a rocket science, but we just haven't come around to do it yet. The other prettier solution is to use something called penalized splines. via linear mixed models. And this is also one of the reasons why I went to Julia in the first place, right? To use this linear mixed models, because I knew you could just use many basis functions and then treat them as if they are a random effect. This is now complex, just for people who know what I'm talking about. Treat them as a random effects and automatically estimate how much shrinkage there should be of the coefficients. So there's like it's a type of penalization for large beta coefficients for any of these splines. And there's a kind of a tutorial. We started with it, but we're still in the mess around stage to get this right. But at some point, this will be there. And then you don't have this issue anymore that you manually have to choose the number of splines. Right? Okay. One step at a time. If somebody is super interested and motivated, I'm totally happy to collaborate on this and get this running. I have a notebook that's half ready, but the details are always tricky. Yeah. I'm very happy to support this. Okay. Well, how to do this in Unfold? That's fortunately extremely simple. You basically, the only thing you need to do is you need to add that you're using this package bspline kit, because this is where the basis functions are created. And if you have Unfold loaded and bspline kit loaded, then Unfold knows, oh, there's an extra package. I'm gonna how do you say, unlock new extra functionalities. And then you can use in the formulas, you can use the spline kind of command, and Unfold does the rest for you. And if you use marginal effects, then this will just out of the box just work. If you plot ERP the coefficients, then you will get this, what I said before on this slide. Let me briefly show it. Then you will get this a little bit uninterpretable mess here of coefficients. You will see. You can just try it out if you're interested in it. And that's so much theory for that block. I think we already covered a lot of theory, so I try to keep it a little bit short in general. Happy to take questions. And okay, so there's a question. Does this mean a column in the matrix corresponds to a spline? Wait, I guess this is a question to this slide here. Yeah, I think this is just a terminology question, what you call a spline, whether you call the whole basis set a spline, which I think is typically done, or whether you call one of these things one of the spline functions. So I would say this is one spline function. Exactly, it corresponds exactly to that. So what we had here, one column basically corresponds to one of these. But of course, they are not sampled in this nice iterative way, but they are sampled in wherever this trial has a value, right? Yeah. Thanks for the question. The question is whether I'm aware of any other nonlinear effects that Unfold helped to uncover so far. For sure. So we have René wrote a nice paper on modeling duration effects as well. So you can imagine like duration, reaction times. There are many things in the brain that have a variable duration. And we are just treating it as if any trial has the same brain activity, regardless whether people were answering fast or slow, or whether looking away quickly or looking away slowly. And here's a nice paper. It's a preprint currently under review in Imaging Neuroscience. And yeah, we basically show that this is possible to model as well, and we do find effects of that. Also in fMRI, by the way, for reaction time. Yeah. So thanks for the question. Okay, then let's get started with the exercise 3, and I let Romy take over again.
Excellent. Do, 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 do. Oops.
My micro is also unmuted. I'm ready to answer the questions now. I'll start with the spline question. So the question is, what do you do if the independent variable, so let's say saccade amplitude, has a bimodal distribution, right? And then it really depends how bimodal is. If it's literally two values, then I think it makes little sense to actually implement a spline data set. You could just categorize it more or less. So if there's really little variability between. If it's more like, okay, the histogram shows two bumps, then you actually don't need to do anything because the splines are automatically put to the percentiles of the, so distributed accordingly. It really, in the end, depends on what the functional, like what the actual function is that relates these two things, your independent variable and your EG. So this would be my answer. Yeah. Then there's the question from Olaf about how well can you load other data? And I just very quickly set up a small demo. Actually, it could have been even smaller than this. So I have a Bluetooth notebook here. Can you see that? I can make it a little bit larger. Right? And basically, you can forget all about this because I just had it in there. But I'm just using PyMNE, which is an MNE wrapper, right? And then in MNE, I know there's input-output, read, raw, EGLab. And this is just, I don't know. I was looking for the first set I can find on my computer. There's an EGLab set. It could be also brain vision, etc. Blah blah blah. Doesn't matter, right? This is how you would load it in MNE. And wouldn't that be great if that just works? Tada! Turns out it just works because it. I told you that the interoperability of Julia is really, really good. So this is now, if you look at the type of this should be some kind of Python type. Yeah. So this is a Python type. It's a Python object, but I can just interact with this. I could say get data. Isn't that how you typically do it? Something like that, right? And I would get a Python array out of this, and then I could just convert it to a Julia array, and suddenly I have all the data in Julia. So this would be one simple way you can do it. But it gets more impressive than this, right? Because what you can do is, right, you can also do something like this. And now it gets really interesting because what I haven't run it yet. Well, let's just run it. What's under the hood working is that MNE gets this command plot and runs it as a matplotlib. And matplotlib then is also converted on the fly and included here. Of course, the interactive version of this will be is not possible to implement here in Bluetooth Notebook because it's browser based. But if you would run this from a REPL or so, I think even the interactive displays should work. The literally only issue I had so far to get this working was when you do animations with MNE. Under certain circumstances, we had only a white image and not a colored image or something like that. I don't know. But so far, this is going well. And then, of course, you could do all the resample 100 hertz filter operation. I don't know the commands now. Everything is possible here. And this is just a Python object, right? So now we have resampled it immediately. And that's why I like, right? So there's yeah, if you know MNE already, then this is easy to use, and else all the MNE tutorials also can be applied just from Julia itself. Okay. Now it becomes more tricky. How to import EGLab structures. This I actually don't know because the study structure in EGLab, my issue is that it changed, I think, 2 or 3 times. It changed how and what it was implementing. And my knowledge of the study is like the first implementation of this. So I actually don't know much about the study structure. Yeah, so I cannot comment too much about it. Typically, you would analyze unfold giving any one single subject, and that's just a set file. So that is typically what you would import. not necessarily to study, which I think also combines over subjects. Yeah. Thanks for the question, though. And you can absolutely write an issue if this is something that you need. Write an issue, and yeah, we will try to look into it. Okay. The question is here. So what we're doing here, what PyMNE is actually doing, is installing. Wait, can I even show it? No, it's gone. No, I don't see it anymore. I was hoping I need to but it's installing its own environment, its own Conda environment, and the environment file itself. It's a TOML file that is typically saved in the environment you're working on. Now we are working in Pluto, so everything is a little slightly different. But if you would have a proper project, then you would have a TOML file that just with all the versions for reproducibility. If you want to use your own Python environment, you can also do that because you don't want to have 10 installations of MNE of different versions installed or something like that. You can, there's a way to bend Python call. This is the underlying package. I'm sure there's some way to bend this to your own environment, but I would need to look it up. Yeah, it's somewhere in the documentation. I know this, but I didn't need to do it so far. Yeah. Okay. Oh yeah, and you can also install new packages. Just add them. I don't know. And then it will just add new packages to your environment if you need them. Okay. Oh, you don't actually see what I'm doing, right? So basically, sorry for that. I forgot I didn't share anymore. You could do something like this, and it would just add a new package to the environment. Okay. I think the questions were answered. Oh yeah, the one other person mentioned NeuroAnalyzer. Yes, NeuroAnalyzer exists. It's like it tries to replace MNE basically with all the pre-processing, all of it, and it has also a ton of readers, etc. It's a very, very big package. I haven't used it so far because well, I just use MNE. I don't need to learn new syntax, etc. But that package also looks very, very promising, and recently was got an Journal of Open Source Software article as well. Yeah, so do check it out. It is a quite big package like MNE, one solution to try to resolve all issues, right? Yeah, I posted again. Thank you to Yassir for mentioning that. Yeah. Okay, I think schedule-wise, we are in time. This is going well. And we still have 10 minutes of break. And then we go for my favorite bit, the overlap correction. I think that's a very exciting one. Yeah. Are we ready? Should we continue? Any new questions coming up? I think we addressed everything, so I hope you had a quick break. And we're gonna continue now with the overlap correction part, which is also called infinite response modeling. Do I have a laser pointer? I don't. Why not? No, I have one. Okay. So far, what we've been discussing was, well, good old ERP event structure, right? So what we had was basically you show a stimulus, or we treat everything as if everything is just separated in time, right? Everything is far away. But it turns out that often in many paradigms, especially if you go for more natural environments, everything is happening at the same time, right? So for instance here, what I showed you here from this nice, from the paper with Olaf together, we had a simple design where somebody's looking at these bikes or these faces. And if you can imagine for a second that each of their eye movements elicits an ERP, right? Then these ERPs, they typically go on for longer than the 200 milliseconds that we on average have time until the next eye movement appears, right? So they are overlapping in time with each other. Of course, this is not what this is, if you would know exactly each individual separate one, that would be perfect, but you don't have access to that. You only have access to this overlapping one. And here in this animation that you probably had time to look at, I make the overlap smaller and then I make it larger again. So very similar to this first notebook that you were working on, where there was this minimal overlap, and you could also include the overlap back, add overlap to your data set. And now you can say, okay, so what do I care? I can leave this meeting now because I don't do eye movement research. But this is not only for eye movement researchers, and I will show you a very stark example later. Worked with Romy together. But this is also can happen if you have a very simple P300 experiment where you ask people to do button presses. And probably even you have it in there if you don't ask them to do button presses, but then you don't have an event. So you can have an event onset from your condition, whatever that is, target, non-target, and then you have a response, a button press response. You will typically measure that in the same electrode because everything is measured in everything. And if you, let's say, are faster for targets than for non-targets, which you are typically, then you would get a systematic bias in overlap between these two ERPs, basically. And so, yeah, you should better take care of that. Okay, how do we do this? I have here, I just take this example once more. This is what you're measuring. This would be an ERP without taking anything into account. And I'm now including also effects of covariance. And of course, that would be great, right? Now you have a difference between bikes and faces and all these different places. You can publish 4 papers on that. Perfect. But we would like to know what are the underlying ones. This is just the good old ERP. To drive this point home of why this can be a problem, let's have a look at this animation. If you have no overlap like you're here, then obviously what you're measuring has the same shape as this curve that I simulated without overlap in the first place. If you now add overlap, then this overall ERP shape will differ because you will have before and afterwards, you will have other of these shapes adding activity to that. And depending on the shape of your overlap distribution, this might look different. So now imagine this is your fixation duration or your reaction time, doesn't matter. And you have these 2 conditions and you have a difference between these 2. What that means is that you're basically sampling this orange line at 2 different places, something like this, right? So you have this difference of overlap distributions. And so then overlap artifact starts to crop in because it takes for the bike fixations, it takes a longer time. Like there are less bike fixations or less other fixations back here than for the face fixation, they are closer by. So you have a systematic difference in overlap. this is actually exactly the same effect of why you should also take care of your nonlinear or effects, because here, let's say you have a nonlinear effect on the P1. You also have a distribution of your predictor, and you have a difference between these two, which also means that I'm sampling maybe the one condition I'm sampling here and the other one I'm sampling here. So this would be a difference that is just solely there because I'm looking at the data at on average, at two different saccade amplitudes in this case, right? So summarizing this was our simulation. Maybe we even have a true effect that we are adding now. We had this biased overlap and biased covariate things, so we have all kinds of effects. This is what we saw before. If we fix the overlap, and we will see in a second how we do it, then already this looks much cleaner before and in the end. And if you also fix the covariate, because we include it and we do a marginal effect at the end, then also this effect goes away. And this is, of course, simulated data. So yeah, but you will see in a second how close we are actually to the true data as far as we can tell so far. Now, this one we know already, how does it work, but we have no idea how to do the overlap. And also, it's maybe at first sight, it might be very surprising that you can even do that. Like, what's the magic behind it? What additional feature can we use from the data to actually disentangle all this mess and go from something like here, overlapping, to something like here where we have the individual ones? And I think the key insight you have to have is that what does it mean to have activity here, right? This activity here has, of course, a certain distance to an event, right? And if we think of this hypothetical non-measurable space here, then we know that this event probably or might have activity that will be measurable in the observed, in the overlapping EEG. This activity also can come from a different event further back. And then we know, because Maxwell's equation, etc., everything adds up linearly. So if there's no interactions between the events, let's assume that for now, then we could just say, okay, what we observe here is just the sum of all the activity of all the previous events, but importantly, at different time points. So this is the response after P1, N1. This is somewhere the response in the P3. But here, this is the response in the N1. Right? It is the same event type, so we will have more or less the same shape, except maybe saccade amplitude, nonlinear effects, blah, blah. But thereby we have this. Okay, how does that help us? Now we know, okay, this point is probably the sum of two responses of the brain. We can just assume that. But we don't know the shapes, so we don't know where to put activity to the one or the other event. Luckily, we can find exactly the same activity here in the next event as well. And now here, if you look here, this is a sum of three different events, right? I'm ignoring events that are super far away back. So yeah. So this is a sum of many more events. So here we have this data point, which is a sum of two events, basically. This data point is a sum of two events at different spacings. And that's exactly, because we can do that for all our events, this is exactly where the variability comes in, that overall, if we put up a system of equation, then we can try to pull these things apart and find the solution that best explains the observed data, given that we know the distances of these to the individual events. Now going back and bringing this together with what we learned earlier with the linear model, with the design matrix, etc. So also, why do I put so much focus on the design matrix? Because it will be so helpful to understand this part here. We're doing something slightly different. Before, we had single trials here, epoch data. This is like the thing that you always use in EEG's ERP analyses. But we are going away from that. We have continuous EEG, and this is important. This is really a conceptual difference. We are not actively epoching the data here. We are epoching the data in the linear model, right? So this is continuous EEG data from sample 21 to sample N, right? And next, we're going to build a very, very large design matrix. Instead of fitting one time point, now we have to fit all the time points at the same time, right? And that means multiple things. First of all, an intercept is not only one column, but suddenly it's one column per time point of your, let's say, epoch, your local time epoch. And the continuous effect would also be not only one column, but it would be multiple columns. In this case, it's only 5. it would be a very short EEG, but this is of course an illustration. You would have 500 of those. You would have 500 predictors for, let's say, 500 samples in a 1000 Hertz data set. And not only your columns are many, but the columns have always matched the betas. So here your betas are also many. So here I have 10 betas fitted at the same time. I colored them because one belongs to the continuous slope and one belongs to the intercept here, basically. But we are fitting all of these at the same time. In the end, what we're really doing is we are trying to predict the continuous EEG, which I think is a very ambitious goal to have. And how far we get there, well, we don't know. And of course, we have some residuals because we will not be able to explain all of the brain activity just by a few events that we are specifying in our model. Okay, now the important bit is now what happens in the design matrix. And you get this kind of staircase, we call it staircase function. For people who do fMRI, this is FIR deconvolution. This is nothing new, has been done since the 90s, but maybe even nonetheless interesting. So what happens here? Here we have an event. So we put in, this is this sample here should be explained by this event immediately after the onset. The next column, we shift this by 1, because now this one here should be explained by the event activity that is 1 sample distance from this. And here 3 samples, etc. And the same is here. They are in parallel because this is the continuous value that belongs to this event here. This event here down here has a different continuous value because maybe it's the next maybe it's the next saccade or so, different saccade size. Now there's no overlap, right? We have a certain time window, 5 samples that we're modeling, and we're assuming everything outside of this time window, there's no activity anymore. But what happens now if I push this event closer, right? I can push this closer. Then the design matrix changes, and suddenly one sample is not explained only by an intercept and the continuous predictor, but by this intercept here and by this intercept here again, because now we are in this domain where this first event still explains the sample, but this event already also explains the sample. So this is how we get the overlap correction in. And because at a later stage, this distance between the events will be different, we will always have a different combination of events, and that's what allows us to solve this problem. Yeah. Nevertheless, that is the explanation of why all of this works. There are some technicalities behind it, because as you can see from all these dots, these are all zeros. So this is a very sparse matrix that we have to do. And if you think of how long an EEG signal is, it can be 3 million data points. And then I already mentioned here, let's say 500 predictors per, like 500 columns per effect here, and you have 5 effects. Then suddenly you have 5,000 predictors to estimate and 3 million data points. And that is, of course, where Unfold really shines and where it has its special solvers to address exactly that problem. But all of this works under the hood. There are some tricks that we are nowadays doing that is more for advanced people, where we can put this stuff on the GPU, where we can do other transformations, etc. And we can really trim down the fitting time of these models by, compared to the MATLAB version, a factor of 100. It depends a little bit on the specifics. But yeah, it's really nice to be able to fit a very complex Unfold model in less, 400 channels in less than 2 minutes or something like that. Yeah, there's more on the Unfold website if you're interested in that. How does this now look in the wild, right? So this is a toy example, of course. In the wild, the design matrix would look like something like this. So you have, again, I plotted the same way. So you have time here, and then you always have the staircases depending on, here we have this is just also some kind of simulation with a button press, maybe a button press event, maybe a phase stimulus event. I forgot what the intercept is. Okay, but it doesn't matter. Now you could rightfully say, okay, this is a nice story and it's a nice idea, and it looks pretty, and you can give talks about this, but does that actually make any sense? Does it work? Is there no interaction between this kind of saccades? Like, what can you show me that might convince me that that this is actually something that makes sense? And like, for me, this is I'm so happy this turned out exactly like that. Because now you saw the simulation, now let's go for real data. This is work from Anna Gerd, and she was interested in free viewing of face processing, faces versus other objects if you just look at stimuli. And this is the non-unfolded classical ERP plot, right? And as you can see, yeah, you do get the N170 phase difference, what you'd expect, but there are many other differences that you can see here, right? And so we were ultimately, in the beginning, we were super happy because we thought like, oh, maybe this is some kind of preview effect. You see the face in the periphery, and that's why it changes, etc., blah, blah. But, well, yeah, it turns out otherwise. So if we add the magic of unfold, pling, right, then suddenly the baseline and the ends, all these differences, they completely go away. And the only thing that remains is the N170 phase effect. And for me, that is I mean, if you're a researcher who's interested in whether the lab experiments generalize to the real world, which everybody should be, then this is kind of a dream result, because this is exactly like in a more ecological valid situation where you have eye movements, you get exactly the same result. How awesome is that? Why was now there? Where does this overlap come from? And mostly the reason why this happened was that people, if you show them an image, they will first look at all the faces, and then they will look at the other objects. So there was an overlap, not only a problem between fixations, but also with the stimulus, a very strong bias there, and that explains this early thing. This later, here's more the different eye movements. Okay. I give you another example. I give you 3 examples in total. This is also something, yeah, well, Olaf is there again. This is a study he did some years ago in reading, right? So it's a reading paradigm. You read a sentence, in jedem Haushalt findet man dort, and then there's a keyword here with an invisible boundary. So if you focus your eyes here, in one condition, you would have a valid preview. In another condition, you have like a jumbled preview. And that's exactly the question. What's the difference if you have a valid preview versus non-valid preview? Can you use the peripheral information to help you read a sentence? And once you landed online, the eye tracker measures once you landed on a word, always the word will be displayed. And we are looking at this fixation here. So you're actually fixating the word, and the 2 conditions are just whether you, in the periphery, you saw a correct or an incorrect preview. So valid or invalid preview. And what people generally found since many years is that if you had an invalid preview, then your fixation duration on that word was slower, right? So it was longer. So if you look at the ERP of this effect, then you will have a systematic bias of when the next fixation comes in. Okay, so we have a systematic overlap bias in this experiment. This is what the data look like without unfold. So you have some kind of ERP, and then you have, after 200 something milliseconds, we get 3 different clusters of differences. This is the difference effect here, different curve. And here, this is the ERP image. I don't have too much time, so I will not. If you don't know what an ERP image is, yeah, the trials are sorted by when the next fixation comes in. Right. So now if we do use unfold, then it looks slightly different. So this middle effect kind of went away. You can also see it in the difference curve. And in the ERP image, this next fixation, this is what we are basically were able to remove. And now we could also only look at this, what we are removing. And if we do this, then we can see that that we actually see exactly this systematic overlap difference. We can see it in the only overlapping activity, and this is actually significantly different from each other. This is kind of the difference between these 2 as well, right? So given this is also, for me, seems to be a very sane way how to empirically test this idea. And now for the latest one, this is a study we did together with Romy, and this is, I think, where we steered the bee's nest most strikingly. And there's ongoing discussion whether our analysis is even valid or not. I'm very happy to discuss it here as well. There are some issues. Okay, I can't go into the details. It's a little bit complicated, but I do think it is quite compelling. So what Romy is interested in is decision making. So why do you choose to eat a burrito or eat the chicken during lunch? These kind of questions. And what people have been done in perceptual learning is that they have been using this kind of drift diffusion models, where you assume, oh, you're integrating information for either of your options, and at some point you reach a threshold, and then you're going to do your response. So they were also looking into EG, and at the CPP, they found the CPP effect where for easy decisions or fast decisions, you get this faster ramp up than for slow decisions. And here, this is 4 different data sets. This is kind of the effects that they were looking for. Sometimes they look a little bit more that they reach the same point, but there's a lot of theory behind this, why this does not necessarily have to be the case. And if you do the difference, there's always a difference between having these kind of things. But now, one issue that they have sometimes try to address, but we argue that they have not fully addressed, is that if you have an easy task, then your reaction time will on average be faster. So what that means is that your response and your stimulus will also be closer together. So there will be a lot of overlap between these 2 ERPs. If you have a hard task, then the reaction time is slow, and then also these 2 things will be further away, so you will have less overlap for these 2 things, right? For the ERP, if you look at the ERP like this, time log to the response, for instance. So, well, basically, what Romy figured out, if you apply unfold to this, then these differences, they just vanish, right? We find no significant difference anymore. Maybe there's a little bit something like here. Or at least we can definitely say there's very much a reduction of this kind of effect. This application of unfold is a little bit criticized, and it's a little bit complicated why or why not this is the case. To make a story short, it's if you have a perfect drift diffusion model that there's no jitter between the stimulus and the onset of the ramp and the offset of the ramp, then you would not know, unfold wouldn't know whether to apply, whether to put this activity to the stimulus or to the response. So in a very clinical situation, this unfold would return a little bit nonsense results, or depends on the parameters, can return things. In real world, we argue that this is not so much a problem because there will always be a little bit of jitter and it will always be tuned more to one or to the other one. But yeah, okay. This is definitely a very striking result and something to be explained for this community as well. We would have been actually very happy if this is not the case. Or I think Romy I mean, I'm happy that this is the case so I could work together with Romy. But I think Romy would have just loved to continue on with the drift diffusion models like that. It would be a very nice signal to have in the brain, I think. Okay, anyway, these were the 3 examples I wanted to give you to try to convince you that there is something that you're modeling that is correct, and at least maybe convince you that the lower thing that you see here is a more realistic version of what's going on in the brain than the upper version, which is definitely biased and to some extent, right, from first principles. Okay. Now, how do we do this in Unfold? In Unfold, now we have to, we slightly shift gears. We have to define one more thing. So we had the data before was channel times time points times epochs. Now, you remember, we have to simulate we have to analyze the continuous EEG. So now we have just channel times time or channel times samples. One big matrix. We also still have the events. Now, importantly, we need this column latency. We need to know when an event is happening in your continuous data. So and the latency is always in samples, like in EEG Lab. We still need a formula, and we can define different formulas for different events. We can even define different time windows for events. You will also learn that, but let's not jump ahead. And now we also need to tell Unfold what kind of staircase to use. And this is, I think, most users will just use the FIR basis. You need to provide it a time window. This is a very common question of how long to put it. This is basically what you're, if you're epoching the data, you also have to put a time window. This is basically that time window. You want to capture all the data of this, all the activity of that event. We have a paper on selecting like how bad it is to make it shorter, and it's not that bad. But yeah, I typically recommend just to have the whole thing there. And you have to provide a sampling rate so that it can translate these kind of numbers to samples, because all the Unfold toolbox pretty much is in samples, except some of the input functions. For convenience, we allow to place some seconds or milliseconds, whatever, here seconds in this case. Then what changes is that instead of the times vector, we now put the basis vector here in the end, and that's it. And I found a mistake here. This should not be data epochs, but this should be data. Sorry for that. Okay. But yeah, you get the point. And in the exercise, of course, you get some hints of how to do it. After you have the model, actually, everything is pretty much the same. You can use CoRFM and you can use CoRF table. Here you will get, you will get slightly different output because now all the betas are attached next to each other. We cannot build this nice matrix that we had before because it could be that the different predictors, the different events have different basis functions with different lengths. So yeah, some of your beta strings will be long, others short, etc. Yeah, anyway. You will see that's why I really like this kind of tidy data frames. Yeah, and I think with this, you are ready to start exercise number 4. Questions? Wait, I will also look at questions. Okay. Yeah, I will, to Tom's question, whether the window length need to be the same for every regressor. Okay, so it needs to be the same for every event. I think that only makes sense that if you have an intercept and a continuous variable or so, that they have the same length. But then you will see we have a multi-event exercise also. You can define that the stimulus should have a very long time window after onset and very short baseline, 200 milliseconds or so. But the fixation should look more symmetric, or a button press should even look more to the back. So they can absolutely, different events, I think conceptually make sense that they actually have different window lengths. Yeah. Yeah, perfect. Okay. So let's get this started. And I highly recommend to go through the main tasks also Brazilian.
There's a question in chat. Do you want to take a look at that?
I do have a clarification. Well, I'll do it in the chat.
It's of course
Okay, I feel like it's break time. There are two more things that I briefly wanted to discuss because I haven't discussed it in the slides, and both are relating to overlap correction. So I think now is a good time to just do that. I don't have slides for that, but they're also relatively quick things. One pertains a little bit of what are the assumptions or the things or the limitations. And René is still figuring out the limitations in a project called Break Unfold. But one definite limitation is that if you have no or very, very little jitter between your events in your data set, so the events are in each trial, it's exactly 400 milliseconds distance, then there's no real way to separate these two. You never will know whether the first event or the activity in the middle is actually relating to the first event or relating to the second event, but previous in time, right? So you could assign it to both of them. So you need some kind of jitter in your data for overlap correction to work. I think this is the first point. I think that's important to keep in mind. And the second one is that if you want to have single subject significance values based on this, then this is a little bit tricky. And this is also tricky in fMRI. That's why they use all this kind of whitening and autocorrelation function or so. And the reason is that if you have this one large, big model, that all the residuals, they have a correlation with each other. So you cannot, like, if you would ask the linear model, hey, how many trials did you see? Then it will not know anything about how many events are put in, but it will only know about how many samples it has. And then it says, awesome, I had 3 million trials, right? And all your standard errors will be tiny, tiny, tiny small. Right, this is not the whole truth. Actually, Felix, who's also here today, he did his master thesis on such kind of effect, and we found very mixed patterns. But now I think with Unfold Sim, we should really revisit that. So Felix, if you're up to it, we can do a small simulation study again, repeating your master's thesis now with different tools. But yeah, this can be a problem to find single subject significance values. Yeah, I wanted just for clarity, I want to add that. Now we're ready for the break. We are so much in time. I think this is really very how do you say, unüblich for me. I have a good team keeping me on track. Okay, so we have one final break, right? Romy, you want to take over? Sorry.
Yes, we do have one final break. Hold on, I don't share the wrong window again. Yes, we do have one final break before the lightning talks, right?
Exactly. We will have 4 short talks about at least some parts of the Unfold ecosystem. We cannot talk about all of them, but yeah.
Oh, Tom says group sets, no problem, right?
Yes, exactly. Yeah. It's a replacement for ERPs if you do the two-stage approach.
I was wondering actually, why would you want single subject p-values?
So every time I read an fMRI paper and they talk on and on about whitening and AR, and so I wonder exactly the same thing. I don't know. Now, sometimes it would be nice, right? Sometimes to know whether some things are actually significant within one subject. Yeah.
Oh well. Actually, how long is this break? Let me double check. 15 minutes.
Well, in 10 minutes, we are talking over
Yeah,
time.
no, definitely. I was gonna say, like, so off these 15 minutes, we've already lost 4. So you have 11 minutes left. See you soon.
And of course, you're allowed to continue on with the exercises until you find a rainbow at the end, maybe a pot of gold as well. Who knows? And you can ask.
No,
questions.
break means break. Follow the rules.
Okay.
Just kidding.
Okay, are we back?
So back.
Okay, we're gonna have our lightning talks because I mentioned this very much in the beginning. Oh, I could actually show this. We have not only one toolbox, but you've actually been using already multiple toolboxes. You've been using Unfold, you've been using Unfold Marquee and Unfold Sim. And we have a bunch of other ones, and we just want to briefly talk about them so you get an idea of how this ecosystem has been growing. And I'll start with Unfold Marquee just right now. So this is actually, I must apologize, or Vladimir wants to apologize. He cannot be here because he's on vacation, which is nice. But he made some slides, and he's the maintainer of the Unfold Marquee toolbox, which I have been using unknowingly because that's the one that allows you to do the stuff like plot ERP, etc. Right? So it is a package for R ERP plotting. Somebody keeping track of time? No? Okay. And it builds upon this Unfold, obviously, but also this really nice library, Marquee.jl, which is an extremely high performance plotting library. I tried them all in all languages, literally, because yeah, anyway. And this one is the only one that doesn't crash for my kind of plots. And we are also building upon algebra of graphics, which is similar to ggplot, but it's like it's not the grammar of graphics, but it's the algebra of graphics, right? So it's one step a little bit removed, but it's quite nice. So why Unfold Marquee in the first place? Well, the regression modeling, these models, they can get very quickly very complex. And I think we need really good tools in order to understand them. Oh, and by the way, if you have questions, just write them in the chat. After the 5 minutes, we have time to answer a little bit. So Unfold Marquee is fast. It has this grammar of graphics style mapping for some of the plots. It integrates nicely with Marquee, so using multi-plots like you have in some of the papers, A, B, C, D, etc. We will create one. Is really it's really good and usable, and all the plots are highly customizable. And this tool really it just does plotting, right? There's no other things to get distracted with. And you can also, of course, also use it outside of Unfold things. If you look, we recently had a survey on EG. Maybe some of you also participated in on EG visualization, so thanks for that. And we can still see that mostly people are using or are familiar with EG and EG Lab and Fieldtrip, and also we see that in the yearly citations. But yeah, I made some points earlier of why we moved from MATLAB. MATLAB is expensive. The plotting is not particularly fast, and you can also not really develop well. So yeah, I think there's a space for Unfold Marquee. Okay, let's just give us a brief tour through some of the features. Let's take a results data frame that you got as a CoF table UF output, right? So this is something that you should be familiar slightly now. It has actually, I don't know, how large is it? But these are the columns that you have. So you have columns for CoF name and maybe for standard error, for time, etc. And it's only 135 entries here. We had this plot ERP function already, right? You've seen it by default. It finds in results, it finds the CoF name and puts it as color. It finds the estimate and puts it on the y-axis. So there are some convenience functions implemented already, but you could also make it explicit, right? So you could say, oh, I'm having the mapping. This is similar to ggplots that you put this, oh, I even forgot how it's called. But it's pretty clear, right? X is time, Y is estimate, color is CoF name. I'm going to drop these things again because we don't need it. So now sometimes you want to change stuff, like modify. The CoF name is a terrible name for this, right? It's just a column that comes out of Julia, of Unfold, and maybe you want to add, change the axis or so. And then there are simple ways you can do it. For the axis, you could specify that the X label should be whatever label you want. And for the CoF name, you could just specify like this, oh, I want to rename this, right? Conveniently, other things are also easy to do. The standard arrow you can add, or if you have a data frame for a significance value from where to where, in which condition is something significant, it's easy to add such kind of bars to it. You can also do something that really the power of the grammar of graphics kind of idea. If you define a certain feature here, and if you assign it to a CoF name, like color CoF name, we have the different colors are for different coef names. You can also use line style, but you can also briefly change this. For instance, you want the column to be the different coef name, or the row, or I don't know, layouts. What else is there that you could put? And so you can very easily imagine that you can look at this your data at your kind of this big space, model space, from very different angles, and modulate very quickly of what you want to show on the different axes. So I think this is really helpful, and really I use it every time. I also mentioned that there's this nice layouting tool. So very often you don't have only a single plot that you want to show, but you want to show multiple plots. So I have 30 seconds. Yeah, this will be sporty. Okay. So let's create a figure here, explicitly create a figure. And now we're using this mutating kind of thing. And we say at the first location, let's add this plot here. Okay, we already done that. Now we can do at the second column, we could add the second plot, right? So if I run this, now I have two plots here. And I can also say, oh, now let's add one more here that stretches over two columns. And well, clearly enough, this will look like something like this, where it will be the second row stretching over both columns. Let's just, it's the first time I'm running this. So you can see it like this. And then later I can say, oh, but I want to still modify this function, right? I want to modify this plot, and I can still, like in MATLAB, add new labels here. Oh, okay, this looks terrible now, but okay, doesn't matter. And the cool thing is you can even add stuff to the left or to the minus side of it. So this layouter automatically takes care of that. And maybe the final thing that I want to show, because I think in other languages it's always a pain to do, you want to add these labels here. In Julia, it's relatively easy because you get this kind of plot. So I put this into the subfigure, and then you say, oh, on top left, just add me a new label, right? And that's it. And you can give it whatever label. So doing this such kind of plot, it's just, yeah, much easier than in any other language. I'm going to skip it for time reason. You can modify a lot of stuff. Conclusions is it's customizable, it's fast, easy to use. If you want to help, if something is unclear or so, yeah, please contact us, read the documentation, and thanks a lot for Vladimir for making all of this possible. Okay, and I'm over time, I guess. But, huh?
Minute and a half.
Minute and a half. Okay, no question. Next talk. No other questions. No questions. Other questions? No, thank you.
Okay, hi everyone, I'm Judith and I want to give you an overview of Unfold Sim, our EEG simulation toolbox. But first of all, I want to take one step back and talk about why to simulate EEG data in the first place. So popular use cases are to do power analysis, to test preprocessing and analysis pipelines, or to validate statistical methods. And of course, if you need example data for an EEG workshop. Because as Bena said, all of you have already implicitly worked with simulated data, and all of this was done with Unfold Sim. But like it was all implicit, so now I want to give you a more explicit overview. And so the key features of Unfold Sim are that it's based on regression ERPs that are combined in either continuous or epoch data. And yeah, you also already experienced this feature that you can have overlapping signals, which is really nice to be closer to real data. Moreover, you can also have multi-subject and multi-channel data. And we tried to make Unfold Sim as modular as possible so that the user can choose between existing simulation ingredients, as we call them, or just implement their own to fit it to their needs. To give you a better overview, like how a simulation really looks like, if it's not hidden in a simulation function, is that I will walk you through a simple example where I explain all the simulation ingredients. So the first ingredient is the experimental design. So in this case, we have again the example of bikes versus faces. And there's also a continuous predictor, which could be contrast level, which could either be low or high. And if you specify it in Unfold Sim, you can do this like with different designs. So here it's a single subject design, and you specify a dict with all the experimental factors that you want to manipulate. To get a better view, you can also output the event table. So each row in this event table corresponds to one event. For example, here a face was shown with this contrast level of 1.5. Okay, so there are many more rows. It's just an overview. Okay, having this ingredient, we also need event basis functions. So we need to know what should happen once an event occurs. And there are a few pre-implemented event basis functions which resemble like typical EEG components, for example, a PEV100 or N170, sorry. But you can also then combine them to have more complex signals. And for this example, I chose to have a complex between 3 different components. And of course, you don't want to take them as they are, but you want to combine them with the design. And for this, you can use regression formulas. For example, here, I decided that the N170 should be modulated by image category, such that the response is more negative for faces than for bikes. Then, yeah, having all these components, as the next step, we need an inter-onset distance distribution, or in other words, we need to decide how far in time the events should be apart. And I think we already had a lot of discussions about this. This was called, I think, min overlap before, but it's actually just like the lower and upper bound of the distribution that decides how many samples should be in between. So this is now like I chose a uniform distribution with a lower bound of 100 and also like another 100. So it's between 100 and 200. Okay, so this is like the distribution, but there could also be others, for example, log normal distribution. Like having all these ingredients, the last one is missing, which is the noise specification. In this case, I chose pink noise. And I also plotted it here so that you can see how it looks like. And in the end, like this will be added to the signal. Okay, having all the ingredients, we just mix them together using this simulate function. And that's like what we get out of it, so the resulting data. On the x-axis is time and samples, and on the y-axis is the amplitude. And these colored bars are the event onset, like for the different events, so faces and bikes. And to give you an example how it looks like if I modify certain parameters, I arbitrarily picked 2. So this is the minimal event offset. If I put it higher, then there will be more space between events. Or if I put it to a small range, there will be less space and a lot more overlap. One other thing, for example, is the noise level. If I put it up, then it will get noisier. And also if I put it to 0, maybe that's interesting, then you can actually see like how this is composed of this single ERPs that are then combined. And also here, you can clearly see that there is some overlap. So this was just a simple example, but if this made you curious, I recommend you to check out the documentation or read our JOSS paper. And also we are not done yet, so there are lots of upcoming new features that still have to be merged. So thanks. So I'm happy to take questions. Let's check out the questions. No questions. Okay. Wait.
Actually, there's a question now. How would you define a new event basis function? Could you do that based on existing data, for instance, or from scratch? For example, a C1 response.
So you can either like just supply a vector as the event basis function, or you can also define it as a function. I'm not sure if this still has to be merged, or is it? No. It's merged? Okay. So you can actually then also just define your own function. Just let me go back. So here, instead of like a P100, you could also supply a vector or like define your own function. To try. So I have like, I don't know.
A bit more. This should work. Yeah, it's a very short one. I think that's like the first one. It's like it's just small step function, like going, yeah, 1 to 10. So it's not that exciting, but in principle, you could, yeah, define your function there. I should have made it a bit longer. So my function is just, I think, 6 samples long now. Okay, does this answer the question? Okay, perfect. Okay, I think then we can switch to the next talk. So thanks.
Can I use your thing to time me? Cool.
Just have to switch
Yes,
it up.
it is. Yes. There we go. All right, next talk. Unfold bits. I will tell myself. Yes. Unfold bits is an idea that you usually don't want to analyze only one of your subjects, but you want to analyze an entire data set. And there bits comes into play. And if you don't know what bits is the brain imaging data structure. And in a very, very tiny nutshell, it's a set of rules to organize your data in a human and machine readable way. And if you want to know more, I highly recommend the bits documentation. It's very extensive, and it sort of tries to make sure that you don't do anything wrong in structuring your data. And the thing is, we can make use of this, right? If a data set is follows some rules in a way it's structured, we can just predefine a set of functions that then we can just reuse on any data set that is structured in this exactly in this same way. So, for example, if you want to use unfold bits, I just give you a quick overview. You can just point to any bits folder data. For example, I have the ERP core data set saved somewhere. And then I can look for my data via one function, load it with another, and then I apply an entire unfold analysis, what you learned for today throughout the workshop, in just one other function. I define all the parameters first, and then apply this to all subjects in one go. And in the end, I just have a data frame which gives me the result from all my subjects in the entire data set. But what is actually, it doesn't go on there. But let's look at what is actually happening under the hood here a bit. First, we set up some stuff. So as always, we need the unfold toolbox, and we load unfold bits. These are the tidy data frames that Unfold also uses. You can, if you ever used pandas in Python, that's about the same. And I here you actually used these two plotting libraries to do some visualizations, because technically the data frames do work with Unfold Maki. But I want to do one plot that's a bit more specific, where I show multiple subjects. That's a bit not implemented in Unfold Maki yet, but maybe in the future. So first we need to look for our data. So we have a root path that points to our bit structured data set. And I give this to unfold bits, and then I already say then unfold bits very, very fast. This took 1.1 second, finds all data sets that is in this root path. And here I can already see from the data frame that I'm getting that I have multiple subjects here. Each subject seems to have multiple sessions and tasks, although the sessions and tasks in this data set are called the same for reasons how the author structured this data set. And I already get some warnings about, hey, there's seems to be multiple session, multiple tasks. Do you really want to analyze them all in the same manner? And I decide that no, actually, I'm only interested in this task here. So I can tell unfold bits, hey, I only want actually this task. So I get a data frame with all subjects now. Each subject just has one row and that one task that I wanted. points me to the file where the dataset is. So I don't really have to set up these loops anymore that we all did in earlier EG analysis. And I also get a pointer to the events file, which is part of the bits data structure. And so in this way, I already can have oh, I'm already at 4 minutes. Wow. Then I can very quickly load my data. And under the hood, Unfold Bits loads uses MNE Python. So I get an MNE raw object. It also loads me the events for each of the subjects. And if I want to have a closer look, Unfold Bits gives you a lot of functionality that makes your life a bit easier. So for example, here I can look at all the events of all subjects at the same time, do some plotting, which I'm not going to go into because I don't have time. And then I can just process. If I have all the data loaded, I can just process everything. But I saw earlier that, hey, the data is not even filtered yet. So I want to apply a filter. So I write a quick function on the raw object that I get from loading it with MNE. And this function I can supply to the run unfold function that's here. And then I supply the data frame. I supply these parameters that we have used throughout the workshop today. And then I just run unfold, first the filter, and then unfold on all the subjects, on all the data sets. And whoop, I get some unfold models. I can unpack these again into a coefficient table for all subjects this time. And because this is a tidy data frame, I can just plot this. For example, now I have here the subjects in different colors and the two different event types in different line styles. But if I want to work more with this, I could, for example, also aggregate over all these subjects. And because data frames is a tidy data, follows the tidy scheme, I can just group combine, for example, here over the event names and time and cohesion, and I want to take the mean over the estimate and then get my grand average in the end, and then I can do much more second level analysis with that. And yes, I think I'm not as much over time as Bene. Are there any questions? Wait, I also have a key takeaway slide actually. So yeah, with Unfold Bits, you can find all the paths to all your subjects in the bits data set. You can load it. You can do some MNE pre-processing if you want to, and apply unfold style analysis, and all with tidy data frames. There's a question. What should be the algorithm to perform today's analysis on several subjects? Can you specify what you mean by algorithm? Because I'm not sure I get this question correctly.
Is it like what commands to use or something like that?
The pipeline, what steps to take. So if you want to supply if you have the data from all your subjects in a bits data set, then you can basically do the 4 steps that I just said, and you can you load your data, and then you use you set up your parameters one time, exactly like you did today. And with these parameters, you can do this basis function dictionary that you supply to the run unfold function. And then you give it all the data frames you loaded before, the data frame you loaded before. You supply the parameter basis function dictionary, and that's sort of it. Then you wait. And
the question was relating to pre-processing. That was one.
The pipeline. What? Yeah. Yeah, maybe got the question, but
you can ask.
Well, I did. What would be the algorithm to perform today's analysis on several subjects?
Okay, we need some clarification here.
Yeah.
Let's do the final talk. Thank you, René.
Yes.
And here, take this. Sure, time me, but
Should we just be mindful?
you can remind me. I will not have capacity to think of anything else. Okay, we have one final thing on mixed models. I very briefly mentioned mixed models before. Let's imagine you have this kind of data sets that we were discussing before. You have bikes versus faces. And let's say you have 13 subjects, 11 items, 4 repetitions in total, 1,100 trials. Wait, items? What the heck is an item, right? Oh, one more new thing to learn. But items are really important concept. They come, I think, mostly from psycholinguistics. And if you do an experiment, you're typically using different faces, different words, different sounds, etc. So, for instance, if you have a face stimuli, each face looks slightly different. So, if I show you a face, you will always get an ERP, a single face ERP that looks a little bit different. Yeah, like Romy says, words are people too. So we can play around with this. And what I have here is I have this typical two-stage t-test, so between faces and bikes. And I also have a linear mixed model. And I want to just show you, okay, if I add a fixed effect, right, then the p-values go down. Okay, that's not surprising. If I don't have a fixed effect, so the null hypothesis is true, what happens now if I add more variability between these individual phases, right? What's happening is that the t-test at some point, it gets significant, but the LMM correctly says, nope, there's no fixed effect. It's still at 0, right? So we have an issue here, apparently, that if we have variability in the items, that we have to account for that. And the reason is that if I show you, there's a difference between showing 100 times the same face or 100 times 100 different faces, right? Because the same face will elicit, on average, a more similar ERP for each of the things than if I vary the face that I'm actually showing. Okay, so item effects inflate type 1 errors. This is what you should take away from this. And I think most experiments have item effects to some extent, or other kind of effects that you could model with linear mixed models. Linear mixed models have other benefits as well. You can do missing data or unbalanced designs easily. You can use multiple continuous variables in the interaction, etc., with repeated measures. So you would in a linear mixed model analyze all data at the same time. And of course, well, you can make your analysis more fancy, and then that's all. Right now, with all the deep learning rage, that's a good thing to have complex models, right? Okay, let's simulate using Unfold Sim. Thank you, Judith. 10 subjects here. We reshaped the data a little bit, blah, blah, blah. This is a little bit boring. But we have EEG data here now, 1 channel, 45 time points, 1,000 trials. 1,000 trials, not all the trials belong to the same subject. You can see here we have a column for subject now, and at some point it will flip over to the next one. Okay, after 100 trials, it will flip over to the subject number 2, right? Okay, we now have to define a linear mixed model formula. So then this one, you know already, this part. This part is a little bit new, and I cannot possibly go into the explanation of how exactly to interpret this, but be assured there is some modeling of the item variability and some modeling of the subject variability, what we typically want. Now, the unfold model command actually looks exactly the same that you had before. Like unfold knows that because there is this kind of grouping in there, it should apply per time point linear mixed models and not a linear model anymore. So that's nice. That's convenient. We can also use pretty much the same plot ERP command. Now we just have to tell the plotting command, okay, split up by group, because now we have the fixed effect. So this is what's true, what's really a literal ERP change. And this would be variabilities here, item variability and subject variability. And as you can see here, there is a difference between conditions, blah, blah, blah. I'm not going into the details, but you can see that over time, the variability of the item and of the subject effect varies, right? Unfold mixed model also allows you to do p-value calculations here, for instance, likelihood ratio tests. So I'm going very quickly. If you never heard of likelihood ratio tests for linear mixed models, then this is what you need to take from it. You can do p-values with it. If you have heard of it, then you find that might be convenient that you have functions to do that, and you can do some kind of p-value plot over time. So this is p-value on log scale. And now somebody might argue, oh, okay, but wait, you're doing so many statistical tests. how do you do cluster permutation testing for mixed models? How is that even possible? And thank you for asking this question. Because it's very difficult, but we are actively working on this. So we have two different packages, especially the mixed models permutation package, where we developed a new permutation test for mixed models, so we can do cluster permutation testing, and it's implemented and it works, and you get out some kind of cluster, something like this here, and you even because we're using this fancy cluster depth algorithm, which I think everybody should check out. It's so cool, much cooler than TFCE and the stuff. I think it's a new cool kit. We even get interpretable p-values per time point, even though this is a cluster test. How cool is that? I can even really say this is the p-value of that point, right? Very convenient. Anyway, yeah. There's no warning. Okay. I didn't fix that. Okay. LMMs, I think, can be super important in many situations, especially in psycholinguistics, but I think actually everywhere, but people just don't realize it. And you can fit this mass univariate LMMs in Unfold. And now can I fix this? Do I even have? Isn't there warning? It's warning box. Okay. Okay, warning. More research is needed. Contact me if you're interested to work on this, right? Yeah, thanks. Any questions? We're happy to take them. Okay, this doesn't seem to be the case, but if you get questions later, please. We have extensive documentation. We are really keen to collaborate with people. We have a lot of collaborations already helping out people. If it's just typically it's just an email or an issue or a discussion, GitHub discussion, just reach out. We are very happy to help and spread our knowledge that we already gained. Yeah, and I think back to the studio.
Yay! Amazing. So good. I will do my screen sharing thing. So I don't think we're doing a break now. I think we are actually at the wrap up. So look at all that we've done. Well, when I say we, I actually hold on. So first of all, when I say we, you have to wait a couple slides. I actually mean the people who actually did work. So before we get there, if you have any more questions, please do put them in the GitHub discussion, and we'll follow up on those things. Maybe there are questions you didn't even think of, and you don't think you have questions. Maybe you should check that out in a couple of days anyway to see what really smart things other people asked, and then you can learn some more. We will send you a follow-up questionnaire. Actually, you know what I'm going to do? I'm gonna grab that questionnaire real quick. And drop it in the chat so that when we're done, you can go ahead and give us your feedback. All right. Please fill this out. I will also email you. So if you cannot do this now, maybe you can do it later. The reason we're doing both is because I think there are some people here who actually didn't sign up. And then also there are some people who did sign up, but didn't come today. But we want to hear from everybody. Okay. I hope you had a lot of fun and that you did learn a lot. I'm pretty sure we all did learn a lot. Even the people doing the workshop did learn a lot. So we had a blast. I put more effort into this than I put into anything else. Want to see it again? Here, wait. Excellent. All right. Yes. So big thank you to today's real heroes to the speakers and to the people who have worked tirelessly in the background. You really are all monastery. It was a pleasure to do this with you. I'm incredibly happy. I think that was fantastic, and I hope we can continue to do fun stuff together. All right. There you go. One more time. Here we go. Okay.
Romy, you should also be on that slide because your organization is fantastic and you just give exactly the right spirits to this whole thing. So yeah, we really appreciate it.
Thank you, Bina. I tried to do my part. Anyway, this was really awesome. Thank you so much, everyone, for your attention. If you have anything else you want to share, please do so. We're also happy to, unmute people if they want to be unmuted. Thanks for the love spreading in the comments. We appreciate it. Yeah, anyone else want to say anything? Cool. Well, then I'll just awkwardly sit here. And
I guess if somebody wants to invite us to give a workshop somewhere else, we're also open for that, right?
Right, especially if you can cover the travel costs, right?
Yeah, beach location would be nice, I think.
Yeah.
And and also this year there might be a permanent position coming up. So if you're in the job market of becoming a lab manager, research software engineer, this kind of thing, then yeah, give me a shout out and I'll keep you posted.
Exciting. Permanent. Wow.
Yeah, you should do it, Romy.
I should do it. I can't do it.
Okay. Should we kick these people out or what do we do with them, right?
I don't know what to do.
Yeah. I think they want to be entertained a little bit more. I have something for those who are still there. Romy, you already know it, right? Because I got new glasses recently, right? So and they're very helpful because I have a very complicated setup here, so I can look at two monitors at the same time. It's really useful, right? The live stream is off, right?
Nope.
No. Nice.
We will keep that.
Okay.
All right.
Let's throw them out and we do our co-host party here.
Yes. Let's I'm gonna have to see how I can wait, hold on. Am I gonna do that? This is funny. So we're gonna be randomly kicking people out now. So let's see. I'll start at the bottom. Remove.
But yeah, we will send the materials. They are also on the materials page, but we'll also send them by email again.
So if it gets cut off now, it's because I removed you. So bye.
Can I also remove someone?
You can try. You have to go on people.
Yeah.
And then under more, you have
Wow,
to
it's
set
really remove, entfernen. Wow. Oh, it was already entfernt. Oh, wow, wait. I have to. Wen möchten Sie melden? Nicht melden. Only Felix is remaining. Felix.
Is
how
he
you
allowed to
doing?
remain? Is he allowed to remain?
Yes, he's an.
Okay.
I haven't seen him for a super long time.
Writing up his thesis.
He's writing up his thesis. Look at that.
I was in the break.
That's he's in UK too. He's
Do we
doing.
allow people to
Liverpool.
unmute themselves?
Huh? I
We
think.
allow people to unmute themselves. We can.
Oh yeah, of course. No, wait. If he wants to say something, did he write? No, but I think he's just away from keyboard, right? Wait, we should stop the live stream also.
Very true. Hold on, let me see. I need to remember how to do this.
Oh yeah, 3 people are watching now. Wait, I think I'm 2 actually. Oh my God.
More live stream. Goodbye.
Well, we were